There is a place in our galaxy so cold that it sits only a few degrees above the lowest temperature the laws of physics will allow. Nothing moves there, almost nothing glows. If you held out your hand inside it, the heat would be ripped away from your skin so fast that the warmth of your own body would feel like a dying ember in an ocean of dark. It is colder than the vacuum between the stars. It is colder than the faint afterglow left over from the beginning of everything. And in that frozen, lightless, lifeless dark, something impossible is happening. A star is being born. Hold on to that, because it makes no sense. Stars are the hottest objects most of us will ever think about. The core of our own sun burns at roughly 15 million degrees. A single second of its output could power human civilization for longer than human civilization has existed. And yet, every star you have ever seen, every point of light scattered across the night sky, every sun warming every world we will ever discover, began its life inside a cloud so cold it would make the South Pole feel like a furnace. The hottest things in the universe are born from the coldest. Let that sink in. These clouds have a temperature of around 10 degrees above absolute zero. In the units astronomers use, that is about 10 Kelvin. Translated into something a human body can fear, it is roughly negative 263 degrees Celsius, or about negative 441 degrees Fahrenheit. There is no warmth left in a place like that. There is barely any motion. The atoms themselves are nearly frozen still, and out of that stillness, gravity is quietly assembling a furnace that will shine for billions of years. Think about the gap that has to be crossed. The starting point is 10 degrees above the coldest temperature the universe allows. The finishing point is a core hot enough to fuse atoms together and pour out light for the age of a planet. Between those two states lies a temperature jump of more than 1,000,000-fold. The same parcel of gas has to climb from almost frozen to almost unimaginably hot. And nothing pushes it up that ladder except its own weight collapsing inward. No external furnace lights it. No outside spark ignites it. The cloud heats itself by falling until it catches fire. That is the engine we are going to take apart tonight, piece by piece. So here is the mystery that drives everything tonight. How does a cloud at 10 degrees above absolute zero become a star burning at 15 million degrees? How does the coldest, emptiest, most lifeless material in the cosmos turn itself into the engine that makes life possible? Because everything you are made of came from this process. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, all of it was forged inside stars, and every one of those stars was born inside a cold, dark cloud, just like the ones we are about to step into. You are, quite literally, the child of a frozen cloud that learned how to burn. But it gets stranger. These clouds should not be able to wait. The physics says that a cloud of gas this massive, pulled inward by its own gravity, should collapse almost immediately, in cosmic terms, in the blink of an eye. If that were true, our galaxy would have burned through all its star-making material long ago and gone dark. Yet the clouds endure. They hang in space for millions of years, resisting their own collapse, refusing to fall, as if something inside them is fighting gravity to a standstill. Something is holding the furnace shut, and for decades, nobody could explain what. There is a force in this story that behaves like a villain. It is invisible. It threads through these clouds like a web of unseen wires. It pushes back against gravity, props the cloud up, and decides which clumps of gas get to become stars and which ones never will. We will name it before the night is over. We will watch scientists chase it across half a century, building telescopes that can see heat instead of light, peering into the darkest patches of the sky, trying to catch a star in the act of being born. And what they found in there was far stranger than anyone expected. By the end of tonight, you're going to understand how a cloud colder than empty space collapses into a ball of fire. You're going to understand why most of the gas never becomes a star at all, why some clouds give birth to giants that die in cosmic violence, and others produce nothing but cold, failed embers that never ignite. You're going to understand the invisible forces that fight over every newborn sun, the hidden jets that scream out of baby stars at hundreds of kilometers per second, and the single number that decides whether a cloud will stay dark forever or burst into light. And you're going to understand something about yourself, that the same process we are about to watch, this slow, violent miracle in the dark, is the reason you exist at all. This is not a gentle story. Star birth is one of the most violent events in the universe, hidden behind a veil of dust so thick that for most of human history, we could not see it happening. It involves collapse, heat radiation, and shock waves that can tear other clouds apart. It involves death feeding life, because many of these clouds are only triggered into making stars when a nearby star explodes and slams a wave of pressure into the cold gas. The end of one star becomes the beginning of dozens of others. The universe recycles its dead to make the living. And the stakes could not be more personal. Look up on a clear, dark night away from any city, and you are seeing the survivors of this process. Thousands of stars that made it, that crossed the threshold, that ignited and held. But for every star that lit up, vast amounts of gas never did. The galaxy is breathtakingly inefficient at making stars. Out of all the cold material packed into a giant cloud, only a tiny sliver, a few percent at most, ever becomes a star at all. The rest is blown back out into space, scattered, wasted, returned to the dark to wait for another chance. There is a brutal selection happening inside these clouds, a sorting of winners and losers, and the rules that decide it were a mystery for generations. Why does one clump of cold gas catch fire, while the clump right next to it stays frozen forever? Why are there stars at all, instead of nothing but cold endless cloud? That question is the thread we will follow all the way to the end. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. So tonight we are going to do something that should be impossible. We are going to travel into the coldest, darkest places in the entire galaxy. Places where the temperature hovers a few degrees from the absolute limit of cold, where light barely penetrates, where the gas is so thin that by the standards of any laboratory on Earth, it would count as a near-perfect vacuum. And we are going to watch, step by step, as that frozen nothing pulls itself together, heats up, ignites, and becomes a star. We are going to follow the gravity, the cold, the invisible magnetic web, and the violent jets. We are going to meet the scientists who spent their lives trying to catch this moment, and the telescopes that finally pulled back the veil. And we are going to arrive, at the end, at the most unsettling truth of all, that everything alive owes its existence to a process that takes place in the coldest, deadest dark imaginable. Now, let's begin. To understand how a star is born, you first have to understand the thing it is born from. And for most of human history, nobody even knew that thing was there. They were staring straight at it, night after night, and they thought they were looking at nothing at all. Go back a couple of centuries to the era of the first great telescopes. William Herschel was the finest observer of his age, the man who discovered the planet Uranus, the astronomer who mapped more of the night sky than anyone before him. He spent countless nights sweeping his enormous telescopes across the band of the Milky Way, counting stars, charting the structure of our galaxy by sheer patience. And again, in the middle of those dense star fields, he found patches where the stars simply stopped. Black gaps. Regions where the rich carpet of light gave way to absolute emptiness. Herschel looked at these dark holes in the star clouds and reached the natural conclusion. He believed they were exactly what they appeared to be. Tunnels, openings, genuine gaps in the distribution of the stars. He is said to have called one of them a hole in the heavens, a place where, if you looked, you could see straight out the back of the galaxy into the void beyond. It was a reasonable idea. It was also completely wrong. And the truth, when it finally arrived, would turn out to be one of the most important discoveries in all of astronomy, because those dark patches were not holes. They were the exact opposite. They were not the absence of something. They were the presence of something enormous, something cold, something hiding in plain sight. They were the clouds from which stars are made. The man who began to crack it open was an American astronomer named Edward Emerson Barnard. He came from poverty, taught himself the sky as a boy working long hours in a photography studio, and grew into one of the most gifted observers the field has ever seen. And he had a weapon Herschel never had: the camera. In the closing years of the 19th century and the opening years of the 20th, Barnard turned long-exposure photography onto the Milky Way, and the photographs he produced were unlike anything anyone had seen. They showed the dark regions in exquisite detail, and the more he looked, the less they behaved like holes. A hole would have sharp, random edges. These did not. The dark regions had structure. They had shape. They formed long curling lanes and dense knots and twisting rivers of black that wound through the bright star fields with an unmistakable physical form. They looked, Barnard slowly realized, not like windows onto emptiness, but like clouds, vast obscuring masses of something drifting between us and the stars behind them, blocking the light. Where the cloud was thin, a few faint stars bled through. Where it was thick, nothing got through at all. Barnard catalogued these dark objects one by one, and to this day, the densest of them still carry his name and a number. The famous dark nebula in the constellation Ophiuchus is still called Barnard 68. The pipe-shaped lane of black near the heart of the galaxy is still mapped by his hand. Here is the moment the picture flipped. For a century, astronomers had assumed the dark patches were the boring parts of the sky, empty, lifeless, nothing to study. The reality was the reverse. Those black regions were the most important objects in the entire galaxy, because that obscuring material, that cold, drifting stuff blocking the starlight, was the raw material of every future star. The empty-looking dark was not empty, it was pregnant. Something is wrong with our assumptions, the data was screaming. And it would take another half a century of physics to understand just how wrong and just how much was hiding in there. So what is the cloud actually made of? Strip away the mystery and the answer is almost absurdly simple. It is mostly hydrogen, the lightest and most common substance in the universe, the same element that fuels the sun. By count, roughly 9 out of every 10 atoms in one of these clouds is hydrogen. Most of the rest is helium. And then, in tiny amounts, everything else, carbon, oxygen, nitrogen, silicon, iron, the elements that will one day build planets and oceans and living things, scattered through the gas as a thin seasoning of heavier atoms and microscopic grains of dust. But there is a crucial detail in the word molecular, because these are not just clouds of hydrogen, they are clouds of molecular hydrogen. In the warm, exposed regions of space, hydrogen drifts as lonely single atoms. In the cold, dark heart of these clouds, the atoms pair up. 2 hydrogen atoms bond together into a molecule. And that pairing only happens when it is cold enough and dark enough and dense enough for the fragile molecules to survive without being blasted apart by starlight. The very existence of molecular hydrogen is a sign that you have entered one of the coldest, most sheltered places in the galaxy. These are the regions astronomers call molecular clouds, and the biggest of them are called giant molecular clouds, and the word giant is doing an enormous amount of work. Let me give you a sense of the scale, because the numbers are striking. A single giant molecular cloud can stretch across tens, sometimes hundreds, of light years of space. Remember what a light year is. Light is the fastest thing in existence. In 1 second, it could circle the entire Earth roughly 7.5 times. In 1 year, travelling at that unimaginable speed without ever stopping, it covers a distance of nearly 10 trillion kilometers, a single light year, and a giant molecular cloud can be 100 of those across. If you could somehow board a beam of light and fly from one edge of a large cloud to the other, you would travel for a century before you came out the far side. These are among the largest single structures in the entire galaxy, and the mass inside them is staggering. The biggest giant molecular clouds contain enough material to build hundreds of thousands of stars. Some hold more than 1,000,000 times the mass of our sun, all of it frozen, dark and waiting. Picture that. A single cold cloud, drifting silently through the spiral arm of a galaxy, holding within it the raw material for 1,000,000 suns. Every one of those potential suns might one day have its own planets, its own worlds, perhaps its own oceans, all of it locked inside one frozen reservoir of gas, doing nothing, glowing nothing, for ages. Now here is where it gets stranger, because for all that mass, these clouds are almost unimaginably empty. We use the word cloud, and your mind pictures something like a thunderhead, thick and white and substantial. Erase that image completely. A giant molecular cloud is, by any earthly standard, a vacuum. Take the densest, richest cores inside one of these clouds, the parts most ready to form stars, and they still contain only a few tens of thousands of molecules in each cubic centimeter. That sounds like a lot, until you realize that a single cubic centimeter of the air you are breathing right now holds something like 10 quintillion molecules. That is a 1 followed by 19 zeros. The best laboratory vacuum chambers humans have ever built are still denser than the heart of a star-forming cloud. The cloud that will become a sun is emptier than anything we can manufacture on Earth. So how does almost nothing build a star? That is the whole mystery, and the answer is a single word that runs through this entire story like a current: gravity. Even in that near-perfect emptiness, every molecule of gas has mass, and every speck of mass pulls on every other speck. Spread that pull across a cloud the size of 100 light years, across 1,000,000 suns worth of material, and the gentle tug of gravity becomes a force that can crush gas into fire. The cloud is empty, but it is vast, and vastness multiplied by gravity is how the universe builds everything. But before gravity can do its work, there is the cold. And the cold is not a side detail, it is the secret ingredient, the thing that makes the whole process possible. To understand why, you have to understand what temperature actually is. Temperature is motion. Heat is just atoms and molecules moving fast, bouncing, colliding, jittering with energy. The hotter something is, the faster its particles move. The colder it is, the slower they go. And in a molecular cloud at 10 degrees above absolute zero, the molecules have almost stopped moving altogether. They drift. They barely stir. The cloud is so cold that it has lost nearly all of its internal motion. And that stillness is exactly what gravity needs, because the only thing that can hold a cloud up against its own gravity is the outward pressure of its moving particles, the same way the air in a balloon pushes outward to keep the balloon inflated. Heat the gas and the particles fly faster, the pressure rises, and the cloud puffs up and resists collapse. Cool the gas and the particles slow, the pressure drops, and gravity starts to win. The cold is what lets the cloud fall in on itself. The cold is what makes starbirth possible. A warm cloud stays a cloud forever. Only a cold cloud can become a star. The hottest object in the sky requires the coldest possible starting point. That is the central beautiful paradox of this entire story, and we will keep returning to it. How cold exactly? Let me put it in perspective, because the comparison is almost difficult to believe. The natural background temperature of empty space, the faint, ancient warmth that fills the entire universe, the leftover glow described by the leading cosmological model, sits at about 2.7 degrees above absolute zero. That is the floor of the cosmos, the temperature you would measure drifting in the deepest void, far from any star. The cores of molecular clouds are only a few degrees warmer than the absolute cosmic floor. They are among the coldest naturally occurring places that exist. There is one object even colder, the Boomerang Nebula, a dying star some 5,000 light-years away, which an unusually violent outflow of gas has chilled to about 1 degree above absolute zero, making it the single coldest natural place ever measured, colder even than the background of space itself. But the Boomerang is a star ending its life. The molecular clouds are where stars begin theirs, and they begin in a cold so deep it sits just a handful of degrees from the lowest temperature the universe permits. For a long time, this cold created an enormous problem for astronomers, a problem that nearly hid these clouds from science forever. Because here is the cruel trick of physics. Molecular hydrogen, the main ingredient, the substance that makes up the overwhelming bulk of these clouds, is almost completely invisible at these temperatures. It does not glow. It does not emit the kind of radiation that telescopes were built to catch. A cloud could hold 1,000,000 suns worth of hydrogen and shine essentially nothing back at us. The most important material in the galaxy was, for all practical purposes, dark. And it gets worse. Not only does the hydrogen not glow, the dust mixed in with it actively blocks the light of everything behind it. So the clouds were doubly hidden, invisible in themselves, and a curtain drawn across whatever lay beyond. For decades, scientists knew the dark clouds were there, but they had almost no way to see inside them. The breakthrough came from a completely unexpected direction, and it is one of the great quiet revolutions in the history of science. If molecular hydrogen will not show itself, you find a spy, a different molecule, a rarer one mixed into the same cold gas. That does glow in a way a telescope can catch. And the perfect spy turned out to be carbon monoxide. The same gas that is poisonous in your home is, in deep space, one of the most useful substances in all of astronomy. Carbon monoxide is far rarer than hydrogen in these clouds, but unlike hydrogen, it emits a faint, specific glow at radio wavelengths, even at temperatures near absolute zero. Wherever you find that glow, you have found cold molecular gas. Find the carbon monoxide, and you have found the hydrogen hiding alongside it. Find the hydrogen, and you have found the nursery of a future star. In 1970, 3 scientists pointed a radio telescope at the Great Nebula in the constellation Orion and detected that telltale glow of carbon monoxide pouring out of the cold gas. 2 of them, Arno Penzias and Robert Wilson, were the same researchers who had, just a few years earlier, accidentally discovered the faint background radiation that fills the whole universe, a discovery that would earn them a place in scientific history. Now, working with their colleague Keith Jeffords, they had opened a second door. They had found a way to map the invisible. Suddenly, the dark clouds were no longer dark to science. With radio telescopes tuned to carbon monoxide, astronomers could trace the cold molecular gas across the entire sky, chart the giant clouds in the spiral arms, and watch the raw material of stars laid out in front of them for the first time. An entire hidden galaxy of cold gas swung into view. And what that hidden galaxy revealed changed everything. Astronomers discovered that molecular clouds are not smooth, featureless blobs. They are violent, tangled, structured things, shot through with filaments, knots, and dense cores, churned by turbulence, threaded with magnetic fields, sculpted by the radiation of nearby stars. Inside a single giant cloud, the gas clumps into smaller and smaller regions, denser and denser, until in certain spots the density climbs high enough that gravity can finally take hold. Those densest spots have a name. Astronomers call them dense cores, or sometimes prestellar cores, and each one is a star waiting to happen. A single giant molecular cloud might contain hundreds or thousands of these cores, each a separate pocket of cold gas, teetering on the edge of collapse, each a potential sun. But the carbon monoxide was only the first spy. To truly map these clouds, astronomers needed to see the other component hiding in the gas, the dust. And the dust turned out to be far stranger and far more important than anyone had guessed. When you hear the word dust, you probably picture something dirty and dull. Forget that. The dust in a molecular cloud is made of microscopic grains, each one far smaller than a single particle of smoke, built from carbon and silicon, essentially soot and sand at the scale of individual molecules. There is not much of it. For every 100 parts of gas, there is only about 1 part of dust by mass, and yet that tiny fraction of dust does something extraordinary. It is the reason the clouds are dark. Those grains absorb and scatter visible starlight so effectively that even a thin haze of them can blot out the brilliant stars behind. The black curtains that fooled Herschel into seeing holes in the heavens were drawn by particles smaller than the period at the end of a sentence. And the dust does something even more important than hide the clouds. It cools them. When a grain of dust absorbs a stray photon of starlight, it warms slightly, then radiates that heat back out as faint infrared glow, carrying the energy away into space. The dust acts like a planet-sized network of microscopic radiators, bleeding warmth out of the cloud, helping drive the temperature down toward that critical 10 degrees above absolute zero. Without the dust, the clouds could not get cold enough to collapse. Those specks of soot and sand are not contaminants. They are the refrigeration system of star birth. In the deepest, coldest, darkest hearts of these clouds, the dust grains do something stranger still. They grow coats. In the frigid dark, atoms and molecules of water, carbon dioxide, carbon monoxide, ammonia and methane drift onto the surface of each grain and freeze there, building up layer after layer of ice. Every microscopic dust grain becomes a tiny snowball, wrapped in a frozen mantle of the very molecules that will one day seed comets, oceans, and possibly life. The James Webb Space Telescope, peering into a cold dark cloud in the southern constellation Chamaeleon, recently took an inventory of these ices and measured the coldest, deepest frozen chemistry ever detected in any molecular cloud: water ice, frozen carbon dioxide, and even more complex molecules, all locked onto dust grains in the dark, waiting. This is not science fiction. The raw ingredients of comets and of water itself were assembled, atom by atom, on frozen specks of dust inside a cloud colder than anything on Earth, long before any star or planet existed there. As radio telescopes and infrared observatories swept across the galaxy, the true architecture of these clouds came into focus, and it was nothing like a smooth ball of gas. In the early 2010s, a European space telescope named Herschel, an observatory built specifically to see the faint heat of cold dust, mapped molecular clouds in unprecedented detail, and what it revealed was that the clouds are laced everywhere with filaments. Long, thin, glowing threads of cold gas winding through the dark like a tangle of cosmic rivers, some of them stretching for tens of light years. And the dense cores, the actual seeds of stars, were strung along these filaments like beads on a wire, like droplets of water along a spider's thread. The discovery reshaped the entire field. Stars, it turned out, do not form just anywhere in a cloud. They form along the filaments, where gravity has already begun pulling the gas into ridges and threads. The cloud organizes itself into a web, and the stars are born at the densest points of the weave. Tucked inside these clouds are some of the most haunting objects in the sky. Small, dense, isolated knots of cold, dark gas that look, against the bright background of the galaxy, like ink blots, like keyholes of pure black. They were studied in detail in the middle of the 20th century by a Dutch-American astronomer named Bart Bok, and they still carry his name. We call them Bok globules. Bok looked at these compact dark clouds and made a bold guess for his time. He suggested that these small black blobs were not empty pockets but cocoons, dense, collapsing clouds in the very act of forming stars, the gas wrapped tightly around something hidden and growing inside. For years it was only a hypothesis. He could not see inside them. The dust was too thick. But Bok was convinced, and late in his life he compared these globules to insect cocoons in the process of metamorphosis, dark, sealed, and hiding a transformation within. He turned out to be right. When infrared telescopes finally pierced the dust decades later, they found, glowing in the heart of many of these globules, the warm seed of a newborn star. The cocoons really were giving birth, and the smallest of these dark globules are humbling to contemplate. Some are only a fraction of a light year across, tiny by the standards of a giant cloud, and yet sealed inside that compact ball of frozen gas is enough material to build a star and a family of planets around it. A single dark speck against the galaxy, no larger in the sky than a grain of pepper held at arm's length, can contain an entire future solar system waiting to switch on. We look at these objects and see nothing but a hole in the light. What is actually there is a world about to be born. The scale of where these clouds sit in our galaxy is worth pausing on, because it brings the whole thing uncomfortably close to home. These star nurseries are not rare, distant curiosities. They drift through the spiral arms of the Milky Way in their thousands. The nearest large one, the Great Nebula in Orion, hangs about 1,300 light-years away. Close enough that you can find it with your naked eye on a clear winter night, as the faint fuzzy patch in the sword of the constellation, Orion. That smudge of light, visible without any telescope at all, is a cloud where thousands of stars are being born right now, and just recently, astronomers found one even closer. Using the ultraviolet glow of molecular hydrogen itself, a team discovered a vast, previously invisible cloud of cold gas, one of the largest single structures in the sky, and among the closest ever found to our own solar system. They named it Eos, after an old mythological figure associated with the coming of the dawn. It had been hanging there, near our cosmic doorstep, for the entire history of astronomy, and we never saw it, because it was too cold and too dark to glow in any light we had thought to look for. The raw material of stars surrounds us, far closer than we ever realized, hidden by the same darkness that fooled the very first astronomers. Once astronomers had carbon monoxide as their tracer, they did something audacious. They set out to map the cold molecular gas of the entire galaxy. Over years of patient observation, radio astronomers swept their instruments across the whole band of the Milky Way, recording the faint glow of carbon monoxide wherever it appeared, and slowly assembled a complete portrait of the hidden cold universe. What emerged was a galaxy laced with thousands upon thousands of molecular clouds, concentrated in the spiral arms, drifting in great complexes, the raw material of every future generation of stars laid bare for the first time. We had spent thousands of years cataloguing the points of light, Now finally, we could see the dark stuff in between, the clouds from which all that light is born. And those surveys revealed something about time that is genuinely difficult to absorb. A molecular cloud is not eternal, but it is ancient by any human measure. It can drift through the galaxy for millions of years, slowly gathering, slowly cooling, slowly tightening, before it ever makes a single star. And then, once star formation begins inside it, the newborn stars eventually turn on their parent. Their radiation, their winds, and ultimately their deaths heat and shred the remaining gas, blowing the cloud apart from the inside, scattering its material back into space to drift and cool and one day perhaps gather again. It is a slow, vast cycle of gathering and dispersal, collapse and return, running across spans of time that dwarf the entire history of life on Earth. The cloud that made the sun did not last. It made its stars, and then it was torn to pieces by them, and its scattered remains have long since vanished into the general gas of the galaxy. We will never find the cloud we came from. It is gone, because that is the part that brings this home. Our own sun was born exactly this way, about 4.6 billion years ago, in a cold, dark molecular cloud drifting through this galaxy. A dense core crossed the threshold and began to fall. Everything we have described, the cold, the dust, the carbon monoxide, the filaments, the collapsing core, happened to the cloud that became our solar system. The sun, the earth, the water in the oceans, the carbon in every living thing, all of it was assembled out of one of these frozen clouds. We are not observers of star formation from the outside. We are its product. When we look into a molecular cloud today, we are looking at a snapshot of our own beginning, replayed in the dark, somewhere across the galaxy, over and over, forever. Let me give you one more comparison to fix the scale in your mind, because it matters for everything that follows. Imagine shrinking one of these giant molecular clouds down until it was the size of the Earth. At that scale, the dense cores, the actual seeds that become stars, would be scattered through it like a handful of marbles dropped into an ocean. The gas between them would be thinner than the cleanest vacuum any human laboratory has ever produced. And yet, given enough time and enough gravity, those few marbles, those few dense knots in an almost empty sphere, will light up the sky. The emptiest places in the galaxy are the birthplaces of its brightest objects. The numbers are striking precisely because they feel impossible. Almost nothing, spread across almost everything, collapsing into almost everything we are. This brings us to the single most important idea in the entire science of star formation. The precise tipping point where a cloud stops resisting and starts to fall. And to find it, we have to go back to a brilliant English physicist working at the very beginning of the 20th century, a man named James Jeans. In the early 1900s, Jeans sat down to ask a deceptively simple question. Take a cloud of gas in space. Two forces are at war inside it. Gravity pulls inward, trying to crush the cloud into a point. Pressure pushes outward, the gas resisting, trying to expand and disperse. Which one wins? Jeans worked through the mathematics and arrived at an answer so clean and so powerful that it still governs everything we understand about how stars are made. He found that for any cloud, at any given temperature and density, there is a critical mass, a threshold. Below that threshold, pressure wins. The cloud is stable. It sits there, holding itself up, doing nothing, possibly for millions of years. But cross the threshold, get massive enough or dense enough or cold enough, and gravity wins decisively. The cloud can no longer hold itself up. It begins to fall inward on itself, and once it starts, it cannot stop. That critical mass is now called the Jeans mass, and the runaway collapse it triggers is called the Jeans instability. It is the trigger on the gun. Sit with what this means, because it is the hinge the whole story turns on. Whether a clump of gas becomes a star is not random. It is decided by a battle between exactly two forces, and the winner is determined by a single number. And notice what lowers that critical mass. What makes a cloud easier to collapse? Cold. The colder the gas, the lower the pressure, the smaller the mass needed for gravity to take over. This is why, of all the things that matter in star formation, temperature sits at the very center. Warm the cloud, and you raise the bar only an enormous mass could ever collapse. Cool it to 10 degrees above absolute zero, and the bar drops and ordinary clumps of gas suddenly find themselves heavy enough to fall. The cold does not just permit star formation. The cold lowers the price of admission. The cold is what lets a modest pocket of gas, no larger than the future sun, cross the threshold and begin its fall toward fire. So now we have the full foundation. We have the clouds, vast, dark, invisible, hundreds of light years across, holding the mass of 1,000,000 suns. We have the cold, just a few degrees above the absolute limit, the secret ingredient that drops the pressure and lets gravity take hold. We have the spy molecule carbon monoxide that finally let us see the invisible. And we have the trigger, the gene's mass, the critical threshold where pressure loses and gravity wins, and a clump of cold gas begins, slowly at first, to fall in on itself toward the birth of a star. There is one more piece of physics worth holding on to before we go further, because it deepens the paradox at the center of everything. As a clump of cold gas begins to collapse, you might expect it to heat up immediately and stop. After all, squeezing a gas heats it. That is how a bicycle pump warms in your hand. But in the early stages of collapse, the cloud has a clever escape valve. The energy released as the gas falls inward gets radiated away by the dust and by molecules like carbon monoxide, carried off into space as faint infrared and radio glow. The collapsing core stays cold, precisely because it is so good at shedding heat. And staying cold means staying low pressure, which means gravity keeps winning, which means the collapse keeps going. The cloud falls and falls, dumping its heat overboard the whole way down, refusing to warm up enough to save itself. Only much later, when the core becomes so dense that the heat can no longer escape, does the temperature finally begin its violent climb toward fire. The cold does not just start the collapse. The cold sustains it. The gas conspires in its own crushing. And this is exactly where the story should end neatly, except it does not. Because once astronomers had the equations of James' genes in hand, they did a simple calculation, and the result made no sense at all. Genes' mathematics did not just say which clouds would collapse, it also predicted how fast. And when you run those numbers, the answer is alarming. A typical giant molecular cloud, left to the pure pull of its own gravity, should collapse in only a few million years. By cosmic standards, that is the snap of a finger. Worse, once it collapsed, it should convert almost all of its gas into stars in one furious burst. If the clouds in our galaxy actually behaved the way the simplest physics says they should, they would have all collapsed long ago. The galaxy would have burned through its entire supply of star-making gas in a single brief frenzy, and then gone dark, sterile, finished, with no new stars ever forming again. But that is not what we see. The galaxy is still making stars right now. At this very moment, steadily, slowly, a few new suns worth of material every year, and it has been doing so for an immense span of time with no sign of stopping. The clouds are not collapsing in a few million years. They are lingering, they are resisting, they are somehow holding themselves up against a gravity that, by the simplest calculation, should have crushed them long ago. Something inside those cold, dark clouds is fighting back. Something is propping them open, slowing them down, rationing the star formation, stretching it out across the ages. The pure physics of gravity and cold cannot explain it. Think about how strange this really is. We started with a paradox, that the hottest objects are born from the coldest places. Now we have a second paradox stacked on top of the first. The clouds are cold enough to collapse, heavy enough to collapse, and the equations insist they should be collapsing in a frantic cosmic hurry. And yet they are not. They are patient. They are slow. They take their time across millions of years, as if some unseen hand were holding the trigger, refusing to let it fall. The simplest physics gives the wrong answer by a wide margin. And when the simplest physics gives the wrong answer, it means there is a deeper layer of the story that nobody has uncovered yet. There is a missing force in the equations. There is a hidden character in the play who has not yet stepped into the light. And that something, that hidden force standing between the cloud and its own collapse, is the antagonist at the heart of this entire story. To find it, scientists would have to look deeper into the cold than they had ever looked before. They would have to weigh forces they could not see and map fields they could not touch. And what they discovered hiding in the dark would rewrite our entire understanding of how a star is truly born. So there it was, the crime that made no sense. The clouds should have collapsed. The mathematics of James Jeans was clear, clean, and correct, and it predicted that a giant molecular cloud, pulled by its own gravity, should fall in on itself in just a few million years and convert nearly all of its gas into stars in one furious blaze. Run the numbers honestly, and the conclusion is unavoidable. Our galaxy should have spent its entire reservoir of cold gas long ago, in a brief and spectacular fireworks display, and then fallen permanently dark. That is not what happened. The galaxy is calm. It makes only a few suns worth of stars each year, sipping at its gas reserves with maddening patience, and it has been doing so steadily for a span of time, so long it makes the history of life look like a single heartbeat. The clouds are not racing to collapse. They are stalling. They are holding themselves up against their own crushing weight, year after year for 10, 20, 30 times longer than the simplest physics says they possibly can. Something inside them is resisting, and finding out what became one of the central detective stories of 20th century astrophysics. The scientists chasing it behaved exactly like investigators at a crime scene. The victim, the gravitational collapse, was failing to occur on schedule, so they began lining up suspects. What could possibly hold up a cloud heavy enough to make 100,000 suns, cold enough that its own pressure should have surrendered long ago? There were only a handful of candidates, only a few forces in nature capable of pushing back hard enough, and one by one, the investigators put each suspect under the light. The first suspect was simple thermal pressure, the ordinary outward push of the gas, the warmth of the moving molecules. This was the obvious culprit, the one Jeans himself had built into his equations. But it had already been ruled out by the very calculation that created the mystery. Jeans had accounted for the gas pressure when he predicted the rapid collapse. The thermal pressure was already in the math, and the math still said the clouds should fall. The cold gas simply does not push back hard enough on its own. The first suspect had an alibi. The cloud's own warmth could not save it. Something else was at work. The second suspect was far more interesting, and for a while it looked like the whole answer. It was turbulence. Picture the cold gas inside a giant cloud not as something still and serene, but as something violently stirred, churning, swirling, shot through with currents of gas crashing into other currents at terrifying speeds. These are not gentle motions. The turbulent flows inside a molecular cloud can move faster than the speed of sound in that gas. What physicists call supersonic turbulence. And turbulence, like heat, provides a kind of pressure. All that chaotic motion, all those colliding streams of gas, pushes back against gravity and helps hold the cloud open. For a time, many astronomers believed turbulence was the missing jailer, the force keeping the cloud from collapsing on schedule. But turbulence had a problem, and it was a beautiful, contradictory, double-edged problem. Yes, the large-scale churning supports the cloud as a whole, but on small scales, that same turbulence does the opposite. Where two turbulent streams slam into each other, they pile the gas up into dense ridges and knots. Exactly the kind of compressed pockets that are heavy enough to collapse. Turbulence, in other words, is both the jailer and the midwife. On the grand scale, it holds the cloud up and prevents a total collapse. On the small scale, it carves out the very dent cores where individual stars are born. The same force that stops the cloud from collapsing all at once is the force that decides where the stars will form. Everyone who thought turbulence was simply a support against gravity had it half right and half wrong. It was not just holding the cloud up, it was sculpting it. It was choosing the winners, and the turbulence had another flaw as a long-term jailer. It fades. Turbulent motion, left alone, dies out. The energy of all that churning gradually dissipates as the colliding gas radiates its heat away, the same way a stirred cup of coffee eventually goes still. Turbulence in a molecular cloud should decay within roughly the same few million-year span over which the cloud should collapse. So if turbulence were the only thing holding the clouds up, it would run out of strength right about the time gravity needed to be resisted, and the collapse would proceed anyway. The numbers did not add up. Turbulence was part of the story, a huge part, but it could not be the whole jailer. There had to be another suspect, a stronger one, a more permanent one, and this one was invisible. Here is where the true antagonist of our story finally steps out of the dark. the force that had been hiding in these clouds all along, threading through them like an unseen web, propping them open, rationing the birth of stars, deciding the fate of every collapsing core, was magnetism. Magnetic fields. The same phenomenon that turns a compass needle and sticks a note to your refrigerator runs, on a scale almost impossible to imagine, straight through the heart of every molecular cloud in the galaxy. The fields are faint, far weaker than the magnet on your fridge, weaker even than the gentle magnetic field of the Earth itself. But they do not need to be strong. They need only to be vast, and they are. They thread through hundreds of light years of cold gas in long, taut lines of force, an invisible scaffolding, holding up the entire structure of the cloud. And to understand why this faint, invisible field is the great jailer of star formation, you have to understand one of the strangest facts in all of physics. In the cold gas of a molecular cloud, the magnetic field and the matter are locked together. They cannot move independently. Where the field goes, the gas must follow, and where the gas goes, it drags the field along with it. Physicists call this the field being frozen into the gas. It happens because some of the particles in the cloud are charged, electrically charged ions and electrons, knocked loose by stray radiation, and charged particles are not free to move across magnetic field lines. They are bound to them, forced to spiral along them, chained to the invisible web, and because the charged particles are mixed in with the neutral gas, constantly colliding with it, the whole cloud, charged and neutral alike, ends up shackled to the magnetic field. Now picture what this means for a cloud trying to collapse. Gravity pulls the gas inward, toward the center, but to fall inward, the gas would have to drag the magnetic field lines inward with it, bunching them together, compressing the field, and a compressed magnetic field pushes back. Hard. The more you try to squeeze the field lines together, the more fiercely they resist, like trying to compress a bundle of stiff springs. So, as the cloud tries to collapse, the frozen-in magnetic field fights it every step of the way, propping the gas open, refusing to let it fall. This is the missing jailer. This is the force that holds the clouds up for tens of millions of years against a gravity that should have crushed them in 1 or 2. The invisible web of magnetism is the thing standing between the cold cloud and the fire. But how do you weigh something you cannot see? This was the next great problem the investigators faced. A magnetic field threaded through cold, dark gas gives off no light of its own. You cannot photograph it. You cannot point a telescope at it directly. For a long time, the magnetic web inside molecular clouds was more a theoretical necessity than an observed fact. Scientists were sure it had to be there to explain the slow collapse, but proving it and measuring its strength demanded enormous ingenuity. And the methods they invented to do it are quietly brilliant. The first method exploits a delicate effect discovered more than a century ago. When atoms or molecules sit inside a magnetic field, the light they emit gets split, very slightly, into separate components. The stronger the field, the wider the split. The effect is named after the physicist who first observed it, and it is called the Zeeman effect. By measuring this tiny splitting in the radio glow coming from molecular clouds, a split so small it pushes the very limits of what radio telescopes can detect, astronomers could, for the first time, directly weigh the magnetic field hiding inside the cold gas. The splitting was there. The field was real. The invisible web could be measured, and its strength came out almost exactly where the theory of magnetic support predicted it should be. The jailer had been caught on camera. The second method is even more elegant, and it uses the dust. Those microscopic grains of soot and sand floating in the cloud are not perfectly round. They are slightly elongated, like tiny grains of rice, and in a magnetic field they tend to line up, all of them turning to point the same way, like a vast swarm of compass needles. When background starlight passes through this aligned swarm of grains, or when the grains glow with their own faint heat, the light comes out polarized, its waves vibrating preferentially in one direction, betraying the orientation of the grains, and through them, the direction of the magnetic field. By mapping this polarization across a molecular cloud, astronomers could trace the magnetic field lines directly, drawing the shape of the invisible web stretched across light years of cold gas. And what they saw confirmed the picture. The field lines ran through the clouds in great organized patterns, bending and channeling the gas, sculpting the filaments, holding up the structure. The scaffolding was real, and now we could see its shape. The physicist who gave us the language for this frozen-in field was a Swedish scientist named Hannes Alfvén, who built much of the modern science of how magnetic fields and electrically charged gases interact. A field now called magnetohydrodynamics, a word as intimidating as the physics is elegant. His work was so foundational that he was eventually awarded the highest honor in physics. And astronomers like Lyman Spitzer and Leon Mestel took these ideas and applied them directly to the clouds, working out how a magnetic field threaded through cold interstellar gas would resist the pull of gravity. The picture that emerged was startling. They could calculate a critical condition, much like the gene's mass, but for magnetism. If a cloud's magnetic field was strong enough relative to its mass, the field would win. The cloud simply could not collapse, no matter how cold it was, no matter how heavy. The magnetism would hold it open forever. Such a cloud was called magnetically supported, and it was, in effect, sterile, a vast reservoir of star-making gas that could never make a single star because the invisible web would not let it fall. And that created a brand new crisis. Because if the magnetic fields are strong enough to hold the clouds up, and the observations suggested many of them are, then how do stars form at all? How does the gas ever escape the web? How does anything ever fall? We had solved one mystery only to crash straight into a worse one. The first puzzle was why the clouds do not collapse too fast. Now the puzzle was why they collapse at all. The jailer was too good at its job. If magnetism truly governs these clouds, the galaxy should be full of beautiful, stable, eternal clouds and almost no stars. And yet the sky is full of stars. The web is being beaten. Something lets the gas slip through. But what? And it gets worse, because the answer that scientists eventually found is so slow, so subtle, so quietly strange that it took years to even believe. The gas does not break the magnetic web, it seeps through it, drop by drop, atom by atom, across spans of time so long they are difficult to hold in the mind. Remember why the field is frozen into the gas in the first place. Because the charged particles are chained to the field lines, and the neutral particles are dragged along by colliding with the charged ones. But here is the loophole. The neutral particles are not actually attached to the field. They feel no magnetic force at all. They only stay in place because they keep bumping into the charged particles that are attached. And in the cold, dark, dense core of a molecular cloud, there are very few charged particles. Most of the gas is neutral. The radiation that would knock electrons loose and create ions cannot penetrate the dust to reach the core. So deep inside the densest cores, the chains binding the gas to the field grow thin. The neutral gas can begin, very slowly, to drift inward past the magnetic field lines, slipping through the web while the field stays behind, held up by the few charged particles still chained to it. Physicists gave this slow seepage a name. They call it ambipolar diffusion. And it is the secret trapdoor in the magnetic prison. Sit with how slow this is, because the slowness is the whole point. Ambipolar diffusion is not collapse, it is a leak. The neutral gas oozes through the magnetic field over millions of years, gradually concentrating in the center of the core, slowly raising the density at the heart of the cloud, while the magnetic field is left holding up the thinner gas around it. Drip by drip, the center grows heavier, and the magnetic support there grows weaker, until at last the gas in that tiny central region becomes dense enough that gravity overwhelms what little field remains. And only then, after millions of years of patient seepage, does that central knot finally let go and begin to truly fall. This is the rationing mechanism. This is why the galaxy does not burn through its gas in a single blaze. The magnetic web slows everything down to a crawl, forcing the gas to leak through one slow drop at a time, stretching the birth of stars out across the immense spans of time we actually observe. The jailer cannot hold the gas forever, but it can make it wait, and wait, and wait. For a while this seemed like the complete and satisfying answer. Star formation, the textbook said, is slow and magnetically controlled. The clouds are held up by their frozen-in fields, and stars are born only where and when the gas can finally seep through the web by ambipolar diffusion. It was elegant. It explained the maddening slowness. It explained the rationing. Everyone thought they finally had the answer. But they were wrong, or at least, the picture was far from complete, because when astronomers built better telescopes and looked more closely at real clouds actually forming real stars, the timing did not match. In many regions, stars seemed to be forming faster than the slow drip of ambipolar diffusion could possibly allow. The dense cores did not look like they had been sitting around patiently leaking through magnetic fields for tens of millions of years. They looked young. They looked recent. They looked like they had collapsed in a hurry. And this set off one of the great debates in modern astrophysics, a genuine scientific war that is, in some corners, still being fought today. Is star formation slow, magnetically regulated, and patient, gas seeping through the web drop by drop? Or is it fast, turbulent, and dynamic, clouds collapsing in a rush, driven by the colliding currents of supersonic turbulence, magnetism playing only a supporting role? The slow camp and the fast camp have spent decades arguing, building models, gathering data, and the truth, as is so often the case, appears to lie somewhere in between, different in different clouds, a messy collaboration of gravity, turbulence, and magnetism, all fighting over the same cold gas. In recent years, a third picture has gained ground, one that tries to hold both sides at once. In this view, the whole cloud is gently falling together from the very start, a slow, large-scale gravitational collapse of the entire structure, with the densest regions running ahead and forming stars first, while the rest of the cloud continues to gather and fall behind them. The collapse is global, happening on every scale at once, the big cloud feeding the smaller clumps, the clumps feeding the cores feeding the stars, all of it falling inward together in a great cascade. In this picture, the magnetic fields and the turbulence do not so much hold the cloud up as slow it down and shape where the gas concentrates, while gravity, patient and relentless, draws the whole thing inexorably down. Whether this is the final answer, no one yet knows. Clouds are messy, individual, and varied, and the same cloud can look slow in one region and fast in another. What is clear is that the simple, clean story, a cloud sitting placidly until it tips over and collapses, was far too simple. The reality is a running battle on every scale, magnetism and turbulence, and gravity locked in a struggle that plays out across millions of years, and the stars are what fall out of the chaos. The honest answer is that we still do not fully understand which force is in charge. The investigation is not closed, the case is still open. What is not in doubt is that astronomers have now caught individual cores, poised on the very edge of this transformation, frozen in the instant before the fall. The dark globule Barnard 68, that perfect ink blot of black against the stars, has become one of the most studied objects in the field, precisely because it sits right at the tipping point. Measure it carefully, and you find a ball of cold gas, almost exactly balanced between pressure and gravity, holding itself together, neither dispersing nor yet collapsing, a star caught in the breath before its first heartbeat. Some of these prestellar cores show the faint, telltale signature of gas beginning to fall inward, the first whisper of collapse, detected in the subtle shifts of the radio glow from the molecules within. We are, in effect, watching the slow motion beginning of star birth, catching cores in the act of crossing from stable cloud to falling protostar. And the more of them we find and weigh, the clearer it becomes how delicate the balance is. A core can sit at that threshold for an immense span of time, perfectly poised, doing nothing. And then, triggered by a passing shockwave, or a slow leak through the magnetic web, or the gathering weight of gas raining down on it, it tips, and the fall begins, and cannot be undone. Now suppose a core finally wins. Suppose the gas has seeped through the web, or the turbulence has slammed enough material together, or both, and at last, in one small dense knot at the heart of a great cloud, gravity takes hold and the gas begins truly to fall. What happens next is one of the most dramatic transformations in all of nature, and for decades, working out exactly how it unfolds was its own enormous problem. Some of the first people to truly calculate this, to take a collapsing cloud and follow its fall step by step using the equations of physics, did so with the help of the early computers of the 1960s and 70s. One of the most important was a young astrophysicist named Richard Larson, who ran detailed calculations of how a cloud core collapses and found that it does not fall as a uniform whole. The center runs away first, growing far denser than the outer layers, so that the collapsing core develops a sharp, dense concentration at its heart, long before the rest of it has fallen in. Larson also studied real clouds across the galaxy and uncovered a set of relationships, now known as Larson's laws, connecting the size of a molecular cloud, the speeds of the gas moving inside it, and its density. These relations revealed that turbulence and structure inside clouds follow regular, almost universal patterns, the same from one cloud to the next, hinting at deep rules governing how all of this cold gas behaves. The clouds were not chaotic accidents. They obeyed laws. We were beginning to read the rulebook of star birth. The first person to give us a clean mathematical picture of this collapse was an astrophysicist named Frank Shu, who in the late 1970s published a description so influential it shaped the field for a generation. Before Shu, the natural assumption was that when a core collapses, the whole thing falls at once, every part of it rushing inward together. Shu showed something subtler and stranger. The collapse, he argued, begins at the very center and works its way outward. The innermost gas falls first, draining toward the center and beginning to pile up. Then the gas just outside it, suddenly unsupported, falls in to follow. Then the gas outside that. A wave of collapse spreads outward from the center through the core, like a building falling floor by floor from the bottom up, each layer dropping only when the layer beneath it has gotten out of the way. He called it inside-out collapse, and it meant that at the very heart of the falling core, almost from the beginning, a tiny seed begins to grow, a central concentration of gas, gathering mass as the inside-out wave feeds material onto it from above. That seed is the beginning of a star, but the falling gas carries a curse with it, and this curse is one of the deepest problems in the entire science of star formation. The curse is spin. Everything in the galaxy is rotating, slowly, gently. The great cloud turns, the core turns, the gas has a faint, almost imperceptible rotation, and there is a law of physics that will not be denied: the conservation of angular momentum. It is the same law that makes a spinning figure skater speed up when she pulls her arms in. As the skater draws her mass closer to her axis, she spins faster. Now take a cloud core, slowly turning and collapse it. As the gas falls inward, drawing all that mass toward the center, the rotation must speed up, and not by a little, by an enormous amount. A core that began turning so slowly it would take 1,000,000 years to complete a single rotation, collapsed down toward the size of a star, would be spinning so fast it would tear itself to pieces. The gas can never reach the center. The centrifugal force of that runaway spin would fling it back out long before it could fall onto the growing seed. By the simplest accounting, stars should not be able to form at all. The spin should stop them. This is the angular momentum problem, and the math is striking. If you take the gentle, barely detectable rotation of a typical cloud core and conserve it all the way down to the size of a star, you get a rotation speed thousands upon thousands of times too fast, fast enough that the object would shred itself apart and never become a stable star. And yet stars exist. The sun exists, turning placidly on its axis once a month or so, carrying almost none of the spin it should have inherited. Somewhere between the cloud and the star, almost all of the rotation has to be thrown away. Where does it go? How does the gas get rid of nearly all of its spin so it can finally fall onto the star? For a long time, this was a genuine crisis. The very law of physics that governs falling, rotating gas seemed to forbid the formation of the very stars we see everywhere in the sky. The solution to the spin problem turned out to reshape the whole picture of star birth, and it is the reason planets exist at all. As the rotating gas falls in and the spin accelerates, the gas cannot fall straight to the center. The rotation flings it outward in the plane of the spin, but lets it fall freely along the axis of the spin, where there is no centrifugal force to fight. The result is that the collapsing core flattens. It spreads out into a vast, swirling, rotating disk of gas and dust, with the growing seed of the star buried at its center. The spin that could not be destroyed is instead stored in the disk, a great flat whirlpool of material orbiting the newborn star, each parcel of gas circling at just the speed its rotation demands, unable to fall any closer because of its spin. This is the protoplanetary disk. It is the structure from which planets, moons, asteroids, comets, and oceans will one day be made. The curse of angular momentum did not prevent the star. It built a solar system around it. And yet, in a cruel twist that haunts the field to this day, the magnetic fields threaten to ruin even this solution. Remember that the field is frozen into the gas, dragged along with it as the core collapses. As the gas falls in and begins to spin up, the magnetic field lines, anchored in the slowly rotating outer cloud, act like a brake. They resist the spin, bleeding rotation out of the inner gas and dumping it back into the surrounding cloud. A process called magnetic braking. In principle, this is helpful. It removes some of the cursed spin. But the calculations revealed a horror. If the magnetic braking works as efficiently as the simplest theory says it should, it would remove not just some of the spin but nearly all of it. So completely that the rotating disk could never form in the first place. No disk means no planets, no jets, no orderly machine of star birth. The theorists called it the magnetic braking catastrophe, and it is exactly as serious as it sounds. The field that supports the cloud and the field that enables the star threatens, in the same breath, to strangle the disk before it can be born. Untangling how disks survive the magnetic braking catastrophe, how the field gets disordered or slips just enough to let a disk form anyway, remains one of the genuinely unsolved problems of modern astrophysics. We can see the disks. They are out there, thousands of them, photographed in stunning detail. The theory says they should be far harder to make than they evidently are. Something is wrong with our assumptions, and we are still arguing about what. But the disk only stores the spin. It does not get rid of it, and the gas in the disk still has to find a way to shed its rotation so it can spiral inward and feed the growing star. Here nature deploys some of the most violent machinery in the whole process. The same magnetic fields that held the cloud up now thread through the spinning disk, twisting and winding as the disk turns, building up enormous tension like a spring being wound tighter and tighter. And that wound-up magnetic field finds a release. It launches the gas. Twin jets of material erupt from the poles of the newborn star, from directly above and below the disk, along the rotation axis, screaming out into space at hundreds of kilometers per second. These are not gentle outflows. They are some of the fastest, most concentrated streams of matter in the galaxy, narrow beams of gas, blasting away from the baby star, carrying the excess spin and energy out of the system, allowing the disk gas to finally lose its rotation and spiral inward onto the star. The star clears its own spin by spitting it back into space at terrifying speed. These jets were one of the great surprises of modern astronomy, because for years astronomers saw their effects without understanding their cause. Back in the middle of the 20th century, two astronomers, an American named George Herbig and a Mexican astronomer named Guillermo Haro, independently noticed strange, glowing little patches of light in star-forming regions, knots of luminous gas that did not look like ordinary stars or nebulae. Nobody knew what they were. They were catalogued and named after their discoverers, Herbig-Haro objects, and they remained a puzzle for decades. Only much later did the truth come together. Those glowing knots are the places where the invisible jets from a hidden newborn star slam into the surrounding cold gas of the cloud, shocking it, heating it, making it glow. The Herbig-Haro objects are the scorch marks of star birth, the visible scars left where a baby star's jets are blasting into the dark. We were seeing the wounds long before we understood the weapon, and the scale of these jets is staggering. Some of them stretch for several light years out into space, a beam of gas longer than the distance from the sun to the nearest star, fired from an object that has not even fully become a star yet. So now picture the full machine. At the center, a growing seed of gas gathering mass. Around it, a flattened, swirling disk storing the spin, threading through it all the twisting magnetic field, and blasting out from the poles, twin jets, screaming into the dark, carrying away the excess rotation so the disk can feed the star. All of this is happening inside a dense core, wrapped in so much dust that no visible light can escape, which is why, for almost all of human history, we never saw it. The entire violent spectacle of star birth takes place behind a curtain of dust, in the dark, invisible to the eye. It was only when telescopes learned to see in infrared, to detect heat rather than light, the faint warm glow that can leak out through the dust where visible light cannot, that we finally pulled the curtain back and saw a star being born for the first time. And now, at the center of it all, the seed begins to heat. This is the moment the long cold finally breaks. For the entire collapse up to this point, the gas has stayed cold, dumping its heat overboard as fast as gravity generated it, radiating the energy away into space. But as the central seed grows denser and denser, packing more and more mass into a smaller and smaller space, it reaches a point where it can no longer shed its heat fast enough. The gas in the center becomes so dense that it traps its own warmth. The radiation can no longer escape, and the temperature, which has sat near 10 degrees above absolute zero for millions of years, finally begins to climb, slowly at first, then faster. The collapse is now generating heat faster than the core can release it, and the trapped energy drives the temperature up and up. The seed at the center is no longer just a clump of cold gas. It has become a warm, glowing object, its own gravity squeezing it, its own collapse heating it from within. Astronomers have a name for this object. They call it a protostar, a star before it is truly a star, a furnace that has not yet caught fire. A protostar is a genuinely paradoxical thing. It glows, sometimes brilliantly, but not from nuclear fusion that has not begun yet. It shines purely from the heat of its own collapse, from the gravitational energy released as gas piles onto its surface, hammering down from the surrounding disk at high speed. Each parcel of falling gas slams onto the protostar and gives up its energy as heat and light. The protostar is, in a sense, glowing from the violence of its own construction, and it is deeply buried, still wrapped in the dense cocoon of gas and dust from which it is forming, still feeding, still growing, still gathering mass from the disk and the infalling cloud. Astronomers sort these objects into stages, based on how deeply they are still buried, and how much of their surrounding material remains. The youngest, most deeply embedded protostars, still drowning in infalling gas, are the most hidden of all, detectable only by the heat that leaks out through the dust, and catching them at all required a revolution in how we see the sky. The problem had always been the dust. Visible light, the light our eyes and our oldest telescopes are built for, simply cannot escape the dense cocoon around a forming star. It is absorbed and scattered into oblivion before it can reach us. For centuries, this meant the actual moment of star birth was permanently hidden, walled off behind a curtain we could not see through. But the heat radiated by a warming protostar comes out as infrared, longer wavelength light, invisible to the eye, that slips through the dust far more easily than visible light can. Build a telescope that sees infrared, and the curtain becomes translucent. You can see the warm seed glowing inside the cold, dark cocoon. When the first infrared survey satellites swept the sky in the closing decades of the 20th century, they found them, buried in the hearts of dark clouds and Bok globules, exactly where Bart Bok had predicted, glowed the warm signatures of protostars, newborn objects pouring out heat, still wrapped in their dusty envelopes, caught in the very act of forming. Later, more powerful infrared observatories carried the work further. Space telescope named Spitzer, launched at the start of this century, peered into the dark clouds and revealed protostars and their jets and disks in unprecedented detail. The Herschel Observatory mapped the cold dust and the filaments. And most recently, the James Webb Space Telescope, with its enormous mirror tuned precisely to infrared light, has pierced deeper into the star-forming dark than any instrument in history, photographing newborn stars, their jets, their disks, and even the faint glow of the ices frozen onto dust grains in the surrounding cloud. For the first time, we can watch star birth unfold in something close to its full detail. The veil that hid the process for the entire history of astronomy has at last been pulled back, and what we see inside is more violent, more intricate, and more strange than anyone dared imagine. As the protostar continues to contract and heat, it passes through a dramatic series of internal crises. At a certain temperature, the molecules of hydrogen at its core, those paired-up molecules that define the cold cloud, are torn apart by the heat, ripped back into single atoms. And here is a strange twist. Tearing those molecules apart actually absorbs energy, robbing heat from the core, which causes the center to suddenly lose its support and collapse again, a second sharp implosion, deep inside the already collapsing protostar. The object falls inward once more, smaller and denser and hotter than before. Each stage of the collapse drives the temperature higher. From 10 degrees above absolute zero, the core climbs through hundreds of degrees, then thousands, then tens of thousands, then hundreds of thousands, then into the millions. The same gas that spent eternity as one of the coldest things in the universe is now hotter than the surface of any star you can see, and still climbing. There was a Japanese astrophysicist named Chushiro Hayashi who, in the middle of the 20th century, worked out much of how these young contracting stars behave as they heat up and shrink, charting the path a protostar follows on its way to becoming a true star. His work revealed that young stars, before fusion begins, are large, bright, and cool on the surface, and that they slowly shrink and brighten in their cores as they contract, following a well-defined track as they march toward ignition. The path that a contracting young star follows is now partly named after him. It described the final approach, the last stage of the long fall from cold cloud to burning star, the moment just before the furnace catches. And the whole journey, from cold core to burning star, takes a span of time that depends entirely on the mass of what is being born, and the difference is enormous. A star like our Sun takes its time. From the moment its core begins to truly collapse, through the protostar stage, through the slow contraction, to the instant fusion finally ignites, can stretch across tens of millions of years. A modest, low-mass star, a faint red ember far smaller than the Sun, can take even longer, contracting for 100 million years or more before it settles into stable burning. But the giants are born in a frantic rush. A massive star, dozens of times heavier than the Sun, can collapse, ignite, and switch on its fusion in as little as 100,000 years, a cosmic eye blink. The bigger the star, the faster it is born, and, in another of nature's grim symmetries, the faster it will die. The largest stars race through their entire existence, birth, life, and violent death, in a few million years, while the smallest, faintest stars are born so slowly and burn so frugally that they will still be shining long after the giants have come and gone many times over. The same process, the same cold cloud, the same collapse, produces both the sprinters and the long-distance runners of the cosmos, separated by a factor of thousands in how long they take to be born and how long they survive. And here, the entire story converges on a single number, the temperature at the center, climbing relentlessly upward as the protostar contracts, because there is a threshold waiting. At around 10 million degrees, something switches on that changes everything, something that has not happened anywhere in this entire process until now. At 10 million degrees, the hydrogen nuclei at the core are moving so fast, slamming into each other so hard, that they begin to fuse, to merge together, to fundamentally rearrange into a heavier element, releasing in the process a flood of energy out of all proportion to anything that came before. Nuclear fusion ignites, the furnace catches, and the moment it does, everything stabilizes. The energy pouring out from the newborn fusion at the center creates an outward pressure that finally, for the first time in the entire history of this gas, perfectly balances the inward pull of gravity. The collapse stops, the contraction halts, the object stops shrinking and settles into a stable, steady state, pouring out light and heat from the fusion in its core, holding itself up against its own gravity by the sheer force of the fire it has lit. The protostar is gone. In its place is a star. Take a breath and look at what just happened, because it is almost beyond belief. A clump of gas at 10 degrees above absolute zero, among the coldest, stillest, deadest material in the universe, collapsed under its own weight, dumped its heat into space, leaked through an invisible magnetic web, flung off its spin in screaming jets, fell and fell and fell through millions of years of darkness, heating as it went, until at its center it reached 15 million degrees and caught fire. The cold became the furnace, the dark became the light, and it did it with no spark, no ignition, no outside help of any kind. It lit itself by falling in the dark. But this clean story, collapse, disk, jets, ignition, describes how a star like our Sun is born. And when astronomers tried to apply the same story to the giants, to the rare monster stars, dozens of times more massive than the Sun, the whole thing broke down in the most spectacular way. Because a massive protostar runs into a problem the Sun never faced. It gets too bright too soon. As a massive star gathers its enormous bulk, its core heats, and it begins pouring out staggering amounts of radiation while it is still feeding, still trying to grow. And that radiation pushes back. Light itself exerts pressure, and the flood of light from a massive young star is so intense that, in theory, it should slam into the infalling gas and blow it away, halting the star's growth long before it could reach the giant masses we actually observe. By the simplest accounting, the most massive stars should be impossible. The radiation should switch on and shut the door, stopping the star at a fraction of the size we see in the sky. And yet the giants are out there. Stars tens of times the mass of the Sun, even 100 times, blazing across the galaxy. They formed somehow. The radiation did not stop them. How they beat the radiation is, astonishingly, still not fully settled. The leading idea is that the gas does not fall onto a massive protostar evenly from all directions. Instead, it pours in through the disk, in a dense flattened stream, while the blistering radiation escapes upward and downward through the cleared poles. The gas sneaks in through the doorway, while the light blasts out through the windows. Dense fingers and clumps of infalling material may also punch through the radiation, channeling gas down to the growing star faster than the light can push it back. The James Webb Space Telescope has now peered into the most extreme star-forming clouds near the center of our galaxy and caught massive protostars in the act, each of them already weighing around 20 times the mass of the Sun, while still buried in envelopes of 100 suns worth of gas, still feeding, still defying the radiation that should have stopped them. We are watching the impossible happen in real time, and we still cannot fully explain how it works. And it gets worse, because the most massive stars of all, the true monsters, may not form alone at all, but in violent, crowded clusters, colliding and merging and stealing gas from one another in a chaotic scrum that the simple theory of a single collapsing core never anticipated. The birth of a giant is not a quiet event. It is a brawl. But here's what makes this truly terrifying. The same gravity that built the star never stops. The fire in the core is not a victory over gravity. It is a stalemate, a balance, a standoff that will last only as long as there is fuel to burn. And the moment the fuel runs low, the moment fusion falters, gravity will resume its work and crush the star toward an end that, for the largest stars, is among the most violent events the universe has ever produced. The collapse that made the star is the same collapse that will one day destroy it. And worse still, the newborn star is about to turn on the very cloud that made it. The fire it has lit will not stay contained. It will pour radiation and wind and, for the most massive stars, eventually explosive death into the surrounding cloud, heating it, shredding it, blowing it apart. The star is born from the cloud, and then the star destroys the cloud. Creation and destruction are the same act, separated only by time. And to understand how deep that goes, how the death of one star becomes the birth of the next, and how the entire cycle has been running across the whole history of the cosmos, we have to follow the scientists who went looking for star birth in the wild, who built the telescopes that finally caught it happening, and who discovered, in the act of watching stars being born, a truth about ourselves that nobody was prepared for. For all the theory, all the equations, all the warring camps of slow and fast and global collapse, there is only one way to truly know how stars are born. You have to catch one in the act. You have to find a place where it is happening right now, point the best instruments humanity can build straight at it, and watch. And over the past few decades, that is exactly what astronomers have done. They have gone hunting for star birth in the wild, region by region, telescope by telescope, and each great campaign has been its own story of hope, struggle, and revelation. These are the expeditions into the cold dark, the attempts to drag the secret of star formation into the light. The first place to go, the most famous stellar nursery in the entire sky, hangs in the sword of the constellation Orion. You have almost certainly seen it without knowing what you were looking at. On a clear winter night, below the three bright stars of Orion's belt, there is a fainter line of stars marking his sword, and the middle point of that sword is not a star at all. It is a smudge, a faint, fuzzy patch of light that the unaided eye can just barely resolve. That smudge is the Orion Nebula, and it is a vast factory of star birth, roughly 1,300 light-years away. Close enough in cosmic terms to sit practically next door. It is the nearest place in the galaxy where massive stars are being born in large numbers, and for that reason it has become the single most studied star-forming region in all of astronomy. If you want to understand how stars are made, you go to Orion first. At the heart of the nebula sits a tight knot of brilliant young stars called the trapezium, a handful of massive, blazing newborns, only a few 100,000 to 1,000,000 years old, infants by stellar standards, already pouring out floods of fierce ultraviolet radiation that light up the entire surrounding cloud and make the nebula glow. These are stars caught in the freshness of their youth. And surrounding them, embedded in the glowing gas, astronomers suspected there might be something even more important: the disks. The protoplanetary disks predicted by all the theory, the swirling pancakes of gas and dust around the youngest stars, the structures from which planets are supposed to form. For decades, they were only a prediction. Nobody had ever clearly seen one. Then came the Hubble Space Telescope. In the 1990s, an astronomer named Robert Odell turned Hubble's sharp eye onto the Orion Nebula, and what he found was breathtaking. Scattered across the glowing gas were dozens of small, dark, teardrop-shaped silhouettes, disks of cold dust seen in shadow against the bright nebula behind them, each one a flattened swirl surrounding a newborn star. Odell had photographed the protoplanetary disks directly. He gave them a name, proplids, short for protoplanetary disks, and suddenly the theoretical prediction became a photograph. The disks were real. They were everywhere. The Orion Nebula was littered with hundreds of them, each one a potential solar system in the making, each a place where planets might be assembling at that very moment. We were looking at the birth of worlds. The hope had paid off in the most spectacular way. But Orion also revealed something darker, and this is where the story turns. Those same brilliant trapezium stars that lit up the nebula were also destroying the disks around their smaller neighbors. The fierce ultraviolet radiation pouring out of the massive stars was blasting the delicate proplids, boiling away their gas, eroding them, photographing them mid-evaporation with glowing tails streaming away like comets. Some of the disks were being stripped bare before their planets could even form. Here was the brutal truth of a stellar nursery laid out in a single image. The massive stars are born alongside the small ones, but they do not coexist gently. The giants flood the nursery with destructive radiation, and the disks of their smaller siblings pay the price. Birth and destruction, side by side, in the same cloud, captured in the same photograph. And it raised a haunting question that Orion could not fully answer. How many potential planetary systems are snuffed out in the cradle, destroyed by the radiation of their own stellar siblings before they ever have a chance? The nursery, it turned out, can also be a graveyard. And that tension between the stars that build and the stars that destroy would echo through every region astronomers explored next, because the next place they looked made that destruction visible on a scale that stunned the entire world. In the spring of 1995, two astronomers named Jeff Hester and Paul Scowen pointed the Hubble Space Telescope at a star-forming region called the Eagle Nebula, some 6,500 light-years away, and produced what would become the most famous astronomical image ever taken. 3 colossal columns of cold, dark gas and dust, rising out of the nebula like towers, like fingers, like vast cosmic monuments, glowing at their edges where the light of nearby stars caught them. The world named them the Pillars of Creation, and the image went everywhere, onto posters, onto magazine covers, into the imagination of an entire generation. But behind the beauty was a story of violence, and it is a perfect illustration of how stars are both born and destroyed in the same breath. Those pillars are made of the same cold molecular gas we have been describing all along. Dense, dark, star-forming material, several light-years tall, each pillar large enough to swallow our entire solar system many times over. And they are being sculpted. Just off the top of the image, out of frame, sits a cluster of massive, brilliant young stars. And those stars are pouring out a torrent of ultraviolet radiation, so intense that it is eating the pillars away, boiling the gas off their surfaces, carving them into their dramatic shapes. The pillars are not permanent monuments. They are eroding sculptures, being whittled down by the radiation of nearby stars, their cold gas evaporating into space. The process even has a name: photoevaporation, the boiling away of cold gas by intense starlight. And here is the twist that makes the pillars of creation a perfect parable of star birth. As the radiation eats away the softer gas, it uncovers the densest knots hidden inside the pillars, small, hard cores of especially dense gas that resist the erosion, left standing like boulders in a stream as the softer material around them washes away. Astronomers found these dense knots at the tips of the pillars and gave them a wonderfully strange name: evaporating gaseous globules. And inside some of those globules, shielded for now by their own density, are forming stars. So the very radiation that is destroying the pillars is also exposing and, in some cases, helping to trigger the birth of new stars within them. The destruction and the creation are the same process. The light that boils the cloud away also compresses the densest pockets and hurries them toward collapse. Death feeds life, and there is a final eerie wrinkle. Because the Eagle Nebula is so far away, the light we see left those pillars thousands of years ago. Some astronomers have suggested, based on later observations, that a nearby star may have already exploded as a supernova and sent a shockwave that has by now already destroyed or reshaped the pillars, meaning the famous towers we admire in the photograph may no longer exist as we see them, their light still travelling toward us across thousands of light years. A portrait of something that may already be gone. We are looking at a ghost. This is not science fiction. It is simply the price of looking across such enormous distances. You always see the past, and sometimes the past has already ended. So the great nebulae showed us the disks, the destruction, the sculpting, and the triggering. But there was another expedition entirely, not outward to the giant clouds, but downward, to the very bottom of the scale, to the smallest things that cold clouds can make. And what astronomers found at the bottom turned out to challenge the very definition of what a star is. Here is the question that drove this third expedition. We have said that a cloud collapses, heats, and ignites fusion at around 10 million degrees. But what if it cannot? What if a clump of gas collapses, but it simply is not heavy enough? Not enough mass, not enough gravity, not enough crushing weight at the center to ever drive the temperature up to the ignition point. What happens to a star that tries to be born but fails? The answer is one of the strangest objects in the cosmos, and for decades it was purely theoretical, a prediction with no proof. If a collapsing core has less than about 8% of the mass of our Sun, roughly 80 times the mass of the planet Jupiter, then its core, when it finishes contracting, will never get hot enough to fuse ordinary hydrogen. The furnace is laid, the fuel is there, but the match never strikes. The object glows faintly from the heat of its own collapse, then slowly, over immense spans of time, cools and fades, never having truly ignited. Astronomers gave these failed stars a name. They called them brown dwarfs, objects caught forever in the gap between the largest planets and the smallest true stars, too big to be planets, too small to be stars, born from the same cold clouds but denied the fire at the end. For decades, brown dwarfs were a prediction nobody could confirm. They are dim, they are cold, they give off almost no visible light, glowing mostly in the infrared, fading and cooling as they age. Finding one was like trying to spot a dying ember in a dark forest from miles away. The hunt stretched on for years with nothing but failures and false alarms. And then, in 1995, the same remarkable year as the Pillars of Creation, the dam broke. Astronomers confirmed the first genuine brown dwarfs. One was found drifting in the young Pleiades star cluster, the famous cluster you can see as a tiny dipper of blue stars on a winter night. Another, a faint companion to a nearby star, showed in its light the unmistakable chemical signature of an object too cool to be a true star. The failed stars were real. The prediction was confirmed, and almost immediately, astronomers realized brown dwarfs are not rare freaks. They are everywhere. The galaxy is littered with these failed stars, dim and cooling, born alongside their brighter siblings, but denied ignition. Possibly billions upon billions of them, a vast population of the almost stars, hiding in the dark. But the discovery of brown dwarfs cracked open a far deeper question, and it goes to the heart of how cold clouds make stars at all. If a cloud can make objects as small as 80 times the mass of Jupiter, How small can it go? Where does star formation actually stop? Is there a smallest possible thing a collapsing cloud can produce? And here the modern telescopes have delivered shocks that nobody saw coming. The James Webb Space Telescope, peering into young star-forming clusters, has found free-floating objects with masses down to just a few times the mass of Jupiter. And in one cluster, candidate objects estimated at less than the mass of a single Jupiter, drifting alone in space, bound to no star, apparently formed directly from the collapse of the cold cloud, just like a star, only far, far smaller. Objects the mass of a planet, born like a star, wandering the galaxy with no sun of their own. The numbers are striking, because they push right up against the theoretical limit of how small a fragment of cloud can collapse on its own, and they may even cross it. And then there is the strangest discovery of all. Peering into the Orion Nebula, that same well-studied nursery, the James Webb Space Telescope found something that should not exist. Pairs of planet-mass objects. Two worlds each, only a few times the mass of Jupiter, orbiting each other, drifting free in the nebula, bound to no star at all. Astronomers nicknamed them Jupiter-mass binary objects, and nobody can fully explain them. They are too small to form like stars by the standard theory, yet there they are, in pairs, free-floating, dozens of them, in a single nebula. One of the astronomers who found them admitted that they challenge our theories of both star formation and planet formation at the same time, and that the discovery was, in his words, something the models simply did not predict. Here, at the very bottom of the mass scale, in the smallest things cold clouds can make, the science is still wide open. We do not know how these objects form. We do not know how small starbirth can go. The expedition to the bottom of the scale ended not with an answer, but with a deeper mystery. A reminder that even in the most studied nursery in the sky, the cold clouds are still keeping secrets. There is a pattern hidden in all of this, in the giants and the dwarfs and everything between, and it was first glimpsed by an astrophysicist named Edwin Salpeter in the 1950s. Salpeter studied the masses of the stars and noticed something regular, almost lawful, in how they are distributed. For every massive star a cloud makes, it makes many more medium stars, and for every medium star, many more small ones. Nature overwhelmingly prefers to make small stars. The giants are rare, the dwarfs are common. The failed brown dwarfs may be more common still. This distribution, the relative numbers of stars of each mass that a cloud produces, is called the initial mass function, and it is one of the most important and mysterious patterns in all of astronomy. Because here is what is astonishing about it. It appears to be nearly universal. Whether you look at a nursery in Orion, or a cluster halfway across the galaxy, or the ancient stars that formed long ago, the cold clouds seem to make stars in roughly the same proportions every time. The same preference for the small, the same rarity of the giants. Something about the physics of collapsing cold gas produces the same recipe, over and over, across the entire galaxy and across vast spans of time, and we still do not fully understand why. The cloud has a preferred way of breaking itself into stars, and reading the rule behind that preference is one of the great unfinished tasks of the science. If the great nebulae and the failed stars taught us the range of what cold clouds can make, the next expedition would finally let us see, in breathtaking detail, the place where planets themselves are born. And it required building one of the most ambitious instruments in the history of science, in one of the driest, highest, most forbidding places on Earth. High in the Atacama Desert of northern Chile, on a barren plateau more than 5,000 meters above sea level. So high that the air is too thin to breathe comfortably, so dry that almost no water vapor hangs overhead to blur the sky. Astronomers built an array of giant radio dishes called ALMA, the Atacama Large Millimeter and Submillimeter Array. Dozens of enormous antennas, spread across the desert, working together as a single colossal telescope, tuned to the faint glow of cold dust and gas, exactly the wavelengths that pour out of star-forming clouds and protoplanetary disks. ALMA was built to see the cold. It was built to peer into the dusty disks around newborn stars and reveal what is happening inside them. And when it opened its eyes, it produced an image that rewrote the textbooks overnight. In the year 2014, ALMA pointed at a young star called HL Tauri, a newborn sun, only around 1 million years old, still wrapped in its protoplanetary disk, about 450 light-years away, and the image it produced stunned the entire field. Instead of a smooth, featureless pancake of dust, the disk around HL Tauri was carved into a series of bright concentric rings, separated by dark, empty gaps, like a target, like the grooves of a record, ring after ring of dust, with clean dark spaces swept between them. And the explanation for those gaps was electrifying. The dark gaps are almost certainly being carved by forming planets. Inside that disk, around a star barely 1 million years old, baby planets are already taking shape, sweeping up the dust along their orbits and clearing the gaps we can see. We were looking at planet formation, caught in the act, around a star that was itself barely born. Nobody had expected planets to form so fast, so early. While the star was still a protostar drowning in its disk, the image overturned the assumption that planet formation comes long after the star is finished. It does not. The planets and the star grow up together, at the same time, in the same disk. The hope that drove Alma to see into the disks paid off beyond anyone's expectations, and it pushed the timeline of how worlds are born millions of years earlier than the theorists had dared to guess. There is a question hiding underneath everything we have been describing, and it is so basic that it is easy to overlook. How do we even know that any of these stars are young? When you look up at the night sky, every star looks essentially the same. A fixed point of light, seemingly eternal, unchanged across a human lifetime or 1,000 human lifetimes. Stars do not come with birth certificates. They do not glow with a label that says newborn. So how did astronomers ever work out that certain stars are infants only a few 100,000 years old, while others are middle-aged like our Sun, and still others are ancient relics billions of years older than the Earth? The answer is one of the great detective stories in the history of science, and it is the hidden foundation beneath every nursery image we have admired. The first clues came from a particular kind of troublesome star that refused to behave. In the constellation Taurus, astronomers in the early 20th century kept noticing stars that flickered and varied in brightness in a chaotic, unpredictable way, brightening and dimming on timescales of days and weeks with no regular rhythm. The prototype of these misfits was a star called T Tauri, and so the whole class came to be known as T Tauri stars. For a long time they were simply a curiosity, a category of variable stars that did not fit the neat patterns. But slowly, the truth emerged. These erratic, flickering stars were not old and unstable. They were young, extraordinarily young. Stars that had only recently formed and had not yet settled down into the steady, dependable burning of a mature sun. Their flickering was the restlessness of youth. They were still wrapped in disks of gas and dust, still swallowing material in fitful gulps, still contracting and adjusting, still finding their balance. A T Tauri star is in essence a star in its adolescence past the deeply buried protostar phase, but not yet a settled adult. And crucially, T Tauri stars are almost always found in or near molecular clouds, clustered exactly where the cold gas is densest. That was no coincidence. They were young because they had just been born from the very clouds they were sitting in. The flickering stars of Taurus were the smoking gun, the first clear population of visibly young suns, and they handed astronomers a template for recognizing youth elsewhere. Over the following decades, astronomers assembled an entire toolkit for reading a star's age, and the methods are wonderfully clever. One of the most beautiful involves a fragile element called lithium. Lithium is destroyed easily inside stars. It gets cooked and consumed in the hot interiors as a star ages, so that older stars have very little of it left. A newborn star, by contrast, still carries the full original supply of lithium it inherited from its birth cloud, untouched. So if you measure a star's light, split it into its rainbow spectrum, and find the telltale fingerprint of abundant lithium, you are very likely looking at a young star that has not yet had time to burn it away. Lithium became a kind of cosmic measure of youth, a chemical clock counting down from birth. Another powerful method involves the disk itself. A genuinely young star is still surrounded by its warm protoplanetary disk, and that disk glows with excess infrared light, more heat than the bare star alone could produce. So when astronomers measure a star and find it pouring out a surplus of infrared radiation, that infrared excess betrays the presence of a disk, and a disk betrays youth. Yet another clue comes from simply plotting where a star sits on the great diagram that relates a star's brightness to its temperature. Newly formed stars, still contracting, still settling towards stability, sit in a distinctive zone above and to the right of where settled adult stars live. They are, for their temperature, too bright, too puffed up, because they have not yet shrunk down to their final mature size. Their very position on the chart announces their age. Stack all these methods together: the flickering, the lithium, the infrared excess, the position on the diagram, the association with clouds, the jets and the Herbig-Haro objects flying outward, and astronomers can sort the stars of a young cluster by age with remarkable confidence. This is the invisible scaffolding behind every claim that a nursery is full of newborns. We are not guessing. We have learned to read the ages of the stars. Armed with these tools, astronomers turned them on the nearest stellar nursery to Earth, and it became one of the most studied patches of sky in all of astronomy, in the direction of the constellation Ophiuchus, only around 390 light-years away. Practically next door, by the standards of the galaxy, lies a sprawling complex of dark molecular clouds known as Rho Ophiuchi. Because it is so close, it offers the most detailed view we have of low-mass star formation in action, the quiet birth of stars, roughly like our own sun. It is a tangle of dark, dusty lanes, glowing rims, and embedded young stars in every stage of development, from deeply buried protostars to flickering T-Tauri suns just emerging into view. For generations, Rho Ophiuchi has served as a kind of natural laboratory, the place astronomers go to watch ordinary stars being made under relatively gentle conditions, far from the brutal radiation of the most massive nurseries. It is the nursery that looks most like the one our own sun must have grown up in 4.5 billion years ago, and so it was fitting, almost poetic, that when the James Webb Space Telescope marked its first full year of science operations, the image its team chose to celebrate the anniversary was a portrait of Rho Ophiuchi. Released in July of the year 2023, the photograph showed the nearest star-forming region as no one had ever seen it, a glowing tapestry of around 50 young stars, most of them comparable in mass to our sun or smaller, set against towering curtains of dust, lit up in shades of gold and rust and deep shadow. Some of the young stars in the image were ringed by the dark shadows of their own protoplanetary disks, seen at last in fine detail, and streaking across the frame were dramatic jets of molecular hydrogen, glowing bright, blasting outward from newborn stars. The bipolar outflows we have met again and again, here caught fresh and vivid, marking spots where stars had only recently roared to life and begun firing their excess spin and gas back into the cloud. One particularly spectacular star in the image, roughly the mass of our own sun, was caught in the act of erupting with these outflows, a near-perfect snapshot of what our own sun likely looked like in its violent infancy. To gaze at that image is to look at a mirror held up to our own origins, the closest thing we have to a family photograph of the sun's earliest years. The nearest nursery, finally seen clearly, full of stars being born exactly as ours once was. This is not science fiction. It is the deepest, sharpest look we have ever had at the kind of place we came from. That family photograph raises a haunting question about our own sun. When we look at Rho Ophiuchi and see dozens of young stars crowded together in a single cloud, born side by side, we are seeing something that is almost certainly true of our own origins as well. Stars are not, as a rule, born alone. They are born in groups, in clusters and associations, dozens or hundreds or thousands of them condensing together out of the same giant molecular cloud, in the same span of a few million years. A single massive cloud does not make one star. It fragments and collapses in many places at once, seeding a whole brood of stars that emerge together as siblings, sharing the same birthplace, the same chemical composition, the same moment of creation. And everything we know suggests our sun was no exception. 4.5 billion years ago, our sun was almost certainly born in a cluster, surrounded by hundreds or perhaps thousands of sibling stars, all of them lit from the same cold cloud. So where are they now? Where are the sun's brothers and sisters, the stars that shared its nursery? The answer is one of the quietly melancholy truths of astronomy. They are gone, scattered. Stellar clusters are not permanent. Over hundreds of millions of years, the gentle gravitational tugs of passing clouds, and the slow churning of the galaxy's rotation gradually pull a cluster apart, stretching it, shearing it, until its members drift away from one another and disperse into the general swarm of the galaxy. Our Sun's birth cluster came undone billions of years ago, and its siblings have since spread out all across the Milky Way, smeared around the galaxy's orbit, mingled invisibly among the hundreds of billions of unrelated stars. Somewhere out there, scattered across tens of thousands of light years, are the stars that were born from the very same cloud that made our Sun, and we have lost almost all of them, but not perhaps forever. Astronomers have begun a remarkable hunt for the Sun's long-lost siblings, and the technique is like a kind of cosmic genealogy, because the stars in a single birth cloud all formed from the same well-mixed gas. They should all carry nearly the same detailed chemical fingerprint, the same precise blend of heavy elements, in the same exact proportions, inherited from their shared birthplace. This chemical signature is far more specific than a simple measure of how metal-rich a star is. It is a fine recipe, a barcode written in the abundances of many elements at once. The idea, sometimes called chemical tagging, is to scan vast numbers of stars across the sky, measure their chemical fingerprints in detail, and search for the rare ones whose recipe matches the Sun's so closely that they could only have come from the same cloud. Combine that chemical detective work with precise measurements of how the stars are moving through the galaxy, tracing their orbits backward to see whether they once shared a birthplace, and astronomers can begin to identify genuine candidates for solar siblings. A handful of promising candidates have already been proposed, stars whose composition and motion hint that they may have been born alongside our Sun, only to wander off across the galaxy in the eons since. The search is difficult, and the certainty is low, but the dream is extraordinary. To find, somewhere out among the anonymous stars, a true sibling of the Sun, a star forged from the same cold cloud at the same moment, carrying the same chemical signature of a nursery that vanished 4.5 billion years ago. There is something deeply moving in this. The cloud that made our Sun also made our raw materials, the atoms in the Earth, the water in the oceans, the carbon in our bodies, and it made, at the same time, a whole family of other suns, most of which may host worlds of their own, scattered now to the far corners of the galaxy. We are, in the most literal sense, part of a lost family of stars, separated at birth and dispersed across the Milky Way. Ro Ophiuchi shows us what that family looked like in its first moments, all the siblings still gathered together in the glow of their shared cloud. Our own such gathering ended long ago, its members long since gone their separate ways, and every other young cluster we photograph is a snapshot of that same fleeting togetherness, frozen for us in a moment before the inevitable scattering. The nurseries are temporary. The families they make do not stay together, and yet the stars endure and carry the memory of their birthplace written in their chemistry, long after the cloud that made them has been blown away into the dark. And sometimes the scattering is not gentle at all. In the crowded chaos of a young cluster, where stars are packed close together and gravity is constantly tugging in every direction, encounters between stars can turn violent. 3 or 4 stars passing near one another can fling one of their number outward at tremendous speed, a gravitational slingshot that hurls a star clean out of its birthplace and sends it tearing across the galaxy at tens of kilometers per second, far faster than the leisurely drift of an ordinary star. These are the runaway stars, cosmic orphans cast out of their nurseries by the brute mechanics of close encounters. Astronomers have traced several of them backward along their flight paths and found that their trajectories converge, long ago, on the same region of sky, the great star-forming complex in Orion. Run the clock in reverse, and these scattered runaways come hurtling back together toward a single nursery, the place from which they were violently ejected millions of years ago. It is forensic astronomy at its finest, reconstructing an ancient act of stellar violence from the present-day motions of the stars involved, like tracing bullets back to a single gun. 2 of the most famous of these runaways are a pair of blazing blue stars, now flying through utterly different parts of the sky, in nearly opposite directions, one streaking through the constellation Auriga and the other through Columba, far to the south. Yet when astronomers trace their paths backward, both stars converge on the same point in the Orion region at the same moment, roughly 2 million years ago. The most natural explanation is breathtaking. These two stars were once a pair, locked in orbit, until a close encounter with another massive binary tore the whole system apart and flung the two stars outward in opposite directions, like fragments from a collision. They have been racing apart ever since, two siblings hurled to opposite ends of the sky by a single instant of gravitational violence in their shared nursery. Their flight is a fossil record of an event no human eye witnessed, frozen into the geometry of their motion, waiting patiently across 2 million years for someone with the right tools to finally read it. The runaways are proof, written in motion across the sky, that stellar nurseries are not only temporary but sometimes brutal, that the very gravity which gathers stars together can also tear them apart and fling them into exile. Some of the fastest of these stars will never look back. They are leaving the galaxy's disk entirely, bound for the lonely halo or even intergalactic space, carrying the memory of an Orion birthplace they will never see again. The cloud builds the cluster builds the stars, and then the stars themselves dismantle the very gathering that made them, some drifting quietly away, others hurled out at violent speed into the dark. There is no permanence anywhere in this story, only the brief, luminous moment of creation, and then the long scattering that follows. For all its power, Alma sees the universe in a single kind of light, the faint radio glow of cold dust and gas. To complete the picture, astronomers needed another kind of eye entirely. They needed to see the warm infrared light that leaks out from inside the clouds, the heat of newborn stars buried in their cocoons, the glow of dust warmed by the first stirrings of fusion. They needed an instrument that could stare straight through walls of dust that had blinded every telescope before it. And in the final days of the year 2021, after decades of work and delay, that instrument finally rose into the sky. The James Webb Space Telescope, the largest and most powerful observatory ever flown beyond the Earth, unfolded its golden mirror 1.5 million kilometers from our planet and turned its gaze toward the nurseries of the stars. What it saw changed everything once again. To understand why Webb matters so much for this story, you have to understand the single greatest obstacle that has haunted every attempt to watch a star being born. The obstacle is dust. The cold clouds where stars form are not transparent. They are choked with microscopic grains of soot and silicate and ice, and that dust is extraordinarily good at one thing: blocking visible light. The very light your eyes can see, the light that ordinary telescopes are built to catch, cannot penetrate these clouds. Point the most powerful optical telescope on Earth at the heart of a stellar nursery, and you see a wall, a dark, impenetrable curtain. The most important events in the life of a star, the collapse, the ignition, the first 1,000,000 years, all happen hidden behind that curtain, in a place no ordinary telescope can reach. It is as if nature wrapped the most fascinating process in the cosmos inside an opaque shell and dared us to look inside. But infrared light changes the game. Longer wavelengths of light slip past the dust grains, the way a large ocean wave rolls over a small buoy without being disturbed. The redder the light, the more easily it threads through the gaps between the grains. And so infrared astronomy became the master key that unlocked the nursery door. Where visible light sees a black wall, infrared light sees through it, revealing the glowing protostars and the warm tendrils of gas hidden within. The James Webb Space Telescope was built, above almost everything else, to be the supreme infrared eye, and that makes it the most powerful tool ever devised for watching stars being born. Consider what Webb did to the pillars of creation. When Hubble photographed those towering columns back in the 1990s, it showed us the pillars as dark, opaque silhouettes, dramatic black spires set against the glowing gas behind them. We could see their majestic outlines, but we could not see inside. The interiors were sealed. We knew, in theory, that stars were forming somewhere in those dense knots, but we could not watch it happen. Then, in the year 2022, Webb turned its infrared gaze on the very same pillars, and the dark columns lit up from within. Where Hubble saw black walls, Webb saw the warm red glow of dust, semi-transparent now, with newborn stars scattered through the columns like embers buried in ash. Bright crimson knots blazed at the tips of the pillars and along their flanks. Those are protostars, young suns still forming, still feeding, only a few 100,000 years old, that had been completely invisible before. The wavy, fiery lines streaming off the edges of the pillars were the marks of stellar jets, the bipolar outflows we met earlier, slamming into the surrounding gas. Webb did not just take a prettier picture. It revealed an entire hidden generation of stars that had been there all along, sealed inside the dust, beyond the reach of every instrument that came before. Let that sink in. For nearly 30 years, those infant stars were right there in one of the most famous photographs ever taken, and we simply could not see them. And then there were the cosmic cliffs. Among the very first images released from the James Webb Space Telescope in July of the year 2022 was a photograph that looked like something out of a dream, a glittering landscape that resembled a range of golden mountains at twilight, capped by a sea of glowing mist, sprayed across with thousands upon thousands of stars. It was breathtaking enough to be mistaken for an artist's fantasy, but it was real, and it was a star-forming region called NGC 3324 on the edge of the vast Carina Nebula, some 7,600 light-years away. What looked like mountains were the towering walls of a giant cavity carved into a molecular cloud. What looked like a craggy mountain range was actually the boundary between two worlds. Below the cliffs, the cold, dense, dusty gas of the cloud where stars are being born. Above them, a cavity hollowed out and lit up by the brutal radiation of enormous young stars that had already formed nearby, out of frame, above the top of the image. Those massive stars, with their searing ultraviolet light and their fierce stellar winds, were eating into the cloud from above, eroding it, sculpting it, blasting the gas away. The cliffs are a battlefront, and the tallest peaks in that image stand around 7 light-years high. Let that number settle for a moment. A single one of those wispy golden spires, delicate as smoke in the photograph, is taller than the entire distance from our sun to its nearest neighbouring star. We are looking at structures of almost incomprehensible scale, and yet Webb resolved them in such fine detail that astronomers could pick out individual jets and outflows from individual newborn stars buried in the cliff faces. Dozens of them, evidence of an entire population of infant suns caught in the act of being born, each one announcing itself with a spurt of glowing gas. The cosmic cliffs taught us something profound about how star formation actually unfolds across a whole region. It is not a gentle, isolated process where each star quietly condenses in its own private corner. It is a violent, interconnected drama where the first stars to form reshape the environment for everyone who comes after. The massive stars that carved that cavity are not just sitting there. Their radiation is doing two opposite things at once. On one hand, it is destroying the cloud, photo-evaporating the gas, stripping away the raw material before it can collapse, shutting down star formation. On the other hand, that same radiation is compressing the gas just ahead of the erosion front, squeezing the dense knots, possibly triggering them to collapse and form new stars that might never have formed otherwise. Creation and destruction, driven by the same source, locked together in the same wall of light. This is the paradox at the heart of every great stellar nursery, written across the sky in letters 7 light-years tall. Then Webb showed us something more intimate, and in some ways even more astonishing. A single protostar, alone, caught in a perfect portrait. The object is called L1527, a young protostar buried in a dark cloud in the constellation Taurus, around 460 light-years away. It is extraordinarily young, perhaps only 100,000 years old, which on the cosmic clock is the equivalent of a newborn in its first hours of life. And when Webb photographed it, the image looked like a glowing blue and orange hourglass, two brilliant cones of light meeting at a single pinched waist. That image is, quite simply, one of the clearest pictures ever taken of a star in the act of being born. And every part of it tells a piece of the story we have been tracing. The protostar itself is hidden at the very center, at the narrow neck of the hourglass, completely invisible, buried in its dense collapsing core. Around it, edge-on, is the protoplanetary disk, a thin dark line cutting across the waist of the hourglass. the flattened pancake of gas and dust spiraling inward to feed the growing star, the very disk that the angular momentum problem demanded, must exist, photographed in silhouette. And the two glowing cones, the upper and lower bowls of the hourglass, are cavities, hollows carved out of the surrounding cloud by the outflows blasting away from the star's poles, their inner walls lit up by light leaking out from the buried protostar. We are seeing, in a single elegant image, the disk that solves the angular momentum problem, the outflow that carries away the excess spin, and the dark cocoon of cloud that still hides the star itself. The entire architecture of stellar birth, the whole machine, in one photograph. This is not science fiction. This is a real object, 460 light-years from your eyes, photographed by a telescope built by human hands. But perhaps the most extreme thing Webb has shown us lies in the most hostile place in our entire galaxy, the center. 27,000 light-years from Earth, in toward the heart of the Milky Way, sits a monstrous complex of molecular clouds surrounding the supermassive black hole at the galactic core. The largest and most famous of these clouds is called Sagittarius B2, and it is unlike anything in our quiet stellar neighborhood. It is one of the most massive molecular clouds in the galaxy, containing millions of times the mass of the Sun in gas and dust, and it is a chemical factory of staggering complexity, rich in molecules that form nowhere else in such abundance. And nearby, in a related cloud called Sagittarius B1, and across the whole central zone, star formation is happening under conditions so extreme they should, by every rule we have discussed, make it nearly impossible. The gas there is warmer, more turbulent, more violently stirred, threaded with stronger magnetic fields, and battered by radiation and cosmic rays far beyond anything in the calm suburbs where our sun was born. Everything that resists collapse is cranked up to maximum. And yet the stars form anyway, including enormous, massive stars dozens of times heavier than the Sun, blazing into existence inside envelopes of gas 100 times more massive still. Webb, with its ability to pierce the appalling curtains of dust that lie between us and the galactic center, has begun to catch these massive protostars in the act, glowing in the infrared, deep inside their cocoons. Studying them is like studying how life survives at the bottom of the ocean or inside a volcano. If we can understand how stars manage to form even in the brutal heart of the galaxy, where every condition fights against them, then we are beginning to understand just how unstoppable the process of star birth truly is once it finally gets going. And finally, Webb has let us read the very ingredients of the clouds themselves, molecule by molecule, atom by atom. In one of its most quietly revolutionary observations, the telescope stared through the coldest, darkest part of a molecular cloud in the constellation Chamanelian, a region called Chamanelian 1, around 500 light-years away, and used the light of stars behind the cloud as a backlight, reading the shadows those stars cast as they shone through the icy dust. By measuring exactly which colors of infrared light were absorbed by the cloud, astronomers could identify the precise chemical fingerprints of the ices frozen onto the dust grains in the very coldest, darkest depths, at temperatures barely above 10 Kelvin. And they found a rich inventory: frozen water, frozen carbon dioxide, frozen carbon monoxide, frozen ammonia, frozen methane, and even more complex molecules, including the simplest building blocks of the chemistry that, billions of years later, and worlds away, would assemble into living things. These are the coldest, deepest ices ever measured, and here is why it matters so much for our story. These frozen molecules are not bystanders. They are the raw stockpile from which planets, comets, oceans, and atmospheres are eventually built. The water that fills the oceans of the Earth, the carbon that forms the backbone of every living cell, the very atoms in your body. Much of it was first assembled as ice on the surface of a dust grain in the freezing dark of a molecular cloud, long before the sun ignited, waiting in the cold to become part of a world. Webb let us read that inventory directly, for the first time, in the deepest cold. We are looking at the pantry from which solar systems are made. Put all of these discoveries together: the pillars lit her from within, the cliffs 7 light-years tall, the perfect hourglass of a single newborn star, the impossible nurseries at the galactic heart, the deep frozen ices that will one day become worlds, and a single, overwhelming theme emerges. Everywhere we point our newest and sharpest eyes, the universe is more crowded with starbirth, more intricate, more violent, and more fertile than we ever imagined. Every time we thought we had seen the whole picture, a new instrument peeled back another layer and revealed an entire hidden world underneath. Hubble pulled back the first curtain and showed us the silhouettes. ALMA showed us the cold disks and the forming planets. And Webb has thrown open the door completely, revealing the buried stars, the hidden generations, the chemistry of creation written in ice. And yet, for all of this, for all the breathtaking images and the revolutionary instruments and the decades of brilliant work, the deepest question of all still has not been fully answered. We can now watch stars being born in stunning detail. We can photograph the disks, the jets, the cocoons, the ices. But we still cannot fully explain why it works at all, why the magnetic fields let go when they do, why some clouds collapse and others sit sterile for millions of years, why the universe builds stars in exactly the proportions it does, the same recipe in every galaxy we look at. We have pulled back curtain after curtain, only to find another, deeper curtain behind it. And that brings us to the strangest, most unsettling pieces of this entire puzzle. The parts that, even now, with the greatest telescopes ever built, refuse to make sense. We have come a long way in this story. We began with a paradox, that the coldest places in the universe give birth to the hottest objects in it, and we have traced the whole improbable journey from the dark molecular cloud to the collapsing core, through the disk and the jets and the slow ignition of fusion, all the way to the dazzling images of the newest telescopes. You might think, after all of that the puzzle is essentially solved, that we understand how stars are born. But here is the unsettling truth, the part that working astronomers will admit only in quieter moments. We do not fully understand it. Not really. Not from the ground up. There are mysteries buried in the heart of star formation so deep and so stubborn that they have resisted every advance in theory and technology, problems that the greatest minds and the greatest instruments have circled for decades without ever fully cracking. And the strangest part is that some of these mysteries are hiding in plain sight in the most basic facts about how stars are made. Facts so familiar that we have stopped noticing how bizarre they are. Let us look now at the things that still do not make sense. Start with the single most haunting mystery in the entire field, a regularity so precise and so universal that it should not exist. When a giant molecular cloud collapses and shatters into stars, it does not make stars of just any size at random. It makes them in a very particular mix, a great many small stars, fewer medium stars, and only a rare handful of giants. For every massive star that blazes into being, there are dozens of sun-like stars, and hundreds of small dim red stars, and a great swarm of tiny failed stars below them. This distribution, this recipe for how many stars of each size a cloud produces, is called the initial mass function. And here is the staggering thing, it is almost always the same. Look at a nursery in our corner of the galaxy, and you find this recipe. Look at a nursery on the far side of the Milky Way, in completely different conditions, and you find very nearly the same recipe. Day. Look at clusters in other galaxies entirely, galaxies with different histories and different compositions. The same recipe. Look back across cosmic time at star formation billions of years in the past. Still, to a remarkable degree, the same recipe. The universe seems to build stars according to a single, fixed proportion, again and again and again, in wildly different environments, across billions of years, as if following a blueprint written into the fabric of physics itself. Now stop and ask the obvious question. Why? Why should the proportion be the same everywhere? The conditions in these clouds vary enormously. Different temperatures, different densities, different magnetic field strengths, different amounts of turbulence, different chemical makeups. Star formation is a chaotic, violent, messy process, dependent on a tangle of competing forces that we have spent this entire story trying to untangle. By every intuition, that chaos should produce different results in different places. A hotter cloud should make different stars than a colder one. A more turbulent cloud should make a different mix than a calm one. And yet, somehow, out of all that chaos, the same proportion emerges over and over with eerie consistency. It is as if you took 1,000 different factories, with different workers and different machines and different raw materials in different countries, and found that every single one of them, without coordination, produced exactly the same distribution of products, you would be certain there was some hidden law forcing the result. And that is exactly what astronomers suspect about the initial mass function, that some deep underlying principle of physics is forcing the chaos of star formation to settle every time onto the same outcome. But we do not know what that principle is. Something is wrong with our assumptions, because nothing in our patchwork understanding of collapsing clouds explains why the recipe should be so universal. The most basic fact about the population of stars in the universe, how many of each size get made, is at its root an unsolved mystery. Let that sink in. We can photograph stars being born 400 light years away, and we still cannot explain why they come out in the proportions they do. And it gets worse. Consider the rate at which clouds make stars, or rather, the rate at which they fail to. We established earlier that a cold cloud, left to gravity alone, should collapse with breathtaking speed, free falling into stars in a few 100,000 to a few million years. We also established that something resists, that clouds linger far longer than free fall predicts. But when astronomers measured exactly how inefficient star formation really is, the numbers were shocking. Take a giant molecular cloud, with enough gas to make tens of thousands or even millions of stars. In the time it takes that cloud to collapse under its own gravity, what fraction of its gas actually turns into stars? You might expect most of it. The answer is a few percent, often just 1 or 2%. The overwhelming majority of the gas, 98 or 99% of it, in every free fall time, stubbornly refuses to become a star. The clouds are spendthrift in the worst way, hoarding their material, converting only a thin trickle into stars, while the vast bulk sits idle and is eventually blown away, unused, back into the galaxy. The galaxy as a whole is a wildly inefficient star factory, wasting almost all of its raw material, and the deep question is the same as before, only sharper. Why so little? What holds back the flood? We have met the suspects. Turbulence, magnetic fields, the violent feedback of newborn stars tearing their clouds apart. But assembling those forces into a clean theory that predicts the right efficiency, in the right place, at the right time, has proven maddeningly difficult. The math is striking. Star formation runs at roughly 1% of the speed that gravity alone would dictate, and pinning down exactly why, in a way that works everywhere, remains one of the central unsolved problems in all of astrophysics. Then there is the problem of the giants, the most massive stars, the rare monsters at the very top of the recipe. We touched on this earlier, but it deserves a closer look, because it is one of the most genuinely unresolved puzzles in the whole field. A star builds itself by accretion, by pulling in gas from its surrounding disk and envelope, growing heavier and heavier. But a massive star is so luminous, so blindingly bright even before it finishes forming, that its own radiation pushes outward with ferocious force. Light carries pressure, and the light of a forming massive star is so intense that it should, in theory, blow away the very gas trying to fall onto it. The radiation pressure should slam shut the door, halt the accretion, and cap the star's growth at perhaps 8 or 10 times the mass of the Sun. And yet the sky is full of stars far heavier than that. Stars 20, 50, 100, in extreme cases perhaps 200 times the mass of the Sun. They exist. We can see them. They are real. So how did they get so big, when their own light should have starved them long before they reached such masses? This is the massive star formation problem, and it is genuinely not fully solved. Astronomers have proposed clever escapes. Perhaps the gas falls in through a dense disk, sneaking past the radiation, which escapes more easily out the poles. Perhaps the accretion comes in violent, episodic bursts that overwhelm the radiation before it can react. Perhaps, in the most crowded nurseries, the biggest stars are not built by accretion at all, but by the outright collision and merger of smaller stars, slammed together in the dense heart of a forming cluster. Each idea has support, and the truth may involve all of them. But the honest summary is that we do not yet have a complete, settled theory of how the universe builds its largest stars. The objects that forge the heavy elements, that explode as supernovae, that seed the galaxy with the very atoms of life. We cannot fully explain how they are born. Now let us go to the most alien chapter of all, the one that should disturb our intuitions most deeply. Everything we have discussed so far concerns stars forming today, or in the recent past, from clouds enriched with heavy elements and dust and molecules. The cooling agents we spent so long emphasizing, the dust that radiates away heat, the carbon monoxide and water and other molecules that bleed off energy and let the gas grow cold and dense. All of that machinery depends on the presence of elements heavier than hydrogen and helium, but those heavy elements did not always exist. In the beginning, in the first few 100 million years after the universe was born, there were no heavy elements at all. There was no carbon, no oxygen, no silicon, no iron. There was no dust, because there were no atoms heavy enough to make dust grains. The universe was made of almost nothing but hydrogen and helium, pure and pristine, and utterly without the cooling agents that modern star formation relies on. And from this pristine gas, somehow the very first stars had to form. They are called the first stars, the primordial generation, and we have never seen one. Not one. They are perhaps the single greatest prize in observational astronomy, and they remain just beyond our reach. Think about what it means to form a star with no coolants. We spent this whole story establishing that cold is the secret ingredient, that gas must shed its heat to collapse, that without efficient cooling the gas stays warm and puffed up and resists collapse. The first clouds had almost no way to cool. The only coolant available was a tiny trace of molecular hydrogen, a feeble refrigerant compared to the rich chemistry of modern clouds. And so the first clouds could not cool to the frigid 10 Kelvin of today's nurseries. They stayed much warmer, hundreds of Kelvin. And warmer gas, as we learned, has a much larger Jeans mass. It resists fragmenting into small pieces. The consequence is staggering. The first stars could not break up into the swarm of small and medium stars we see today. Instead, the pristine gas is thought to have collapsed into enormous single objects. Stars not a few times the mass of the Sun, but tens or even hundreds of times more massive, true behemoths, blazing with unimaginable fury. The recipe was completely different in the beginning. The universal initial mass function we marveled at a moment ago, the eternal, unchanging recipe, was not always in force. In the very first generation, the recipe was top-heavy, skewed toward giants, because the universe had not yet manufactured the cold-making ingredients that let it produce small stars. The cold clouds that this entire story is built around did not exist yet. They had to be created, and the only thing that could create them was the death of the first stars themselves. This is the cosmic bootstrap, and it is one of the most beautiful ideas in all of science. The first stars, those pristine giants, lived fast and died young, exploding as titanic supernovae and forging, in their cores and in their death throes, the first heavy elements the universe had ever known. Carbon, oxygen, silicon, iron. These atoms, scattered out into space by the explosions of the first stars, became the raw material for everything that followed. The first dust grains, the first molecules, the first true cold clouds. The death of the first generation seeded the gas with exactly the coolants needed to form the next generation. And that next generation could finally cool, fragment, and produce the smaller, longer-lived stars that fill the universe today. Each generation of stars enriched the gas a little more, lowered its temperature a little further, and shifted the recipe toward the familiar modern mix. The cold molecular clouds we have spent this whole story exploring are not a permanent feature of the universe. They are a late invention, an achievement, built up over billions of years by generation after generation of dying stars manufacturing the very ingredients that make cold possible. We are not just made of stardust. The clouds that make stars are themselves made of stardust, recycled and enriched across cosmic time. And the first chapter of that story, the formation of the very first stars from pristine warm gas, is a chapter we have never directly witnessed. The James Webb Space Telescope was built, in part, to hunt for the faint, distant glow of that first generation, to catch the light of stars forming in a universe with no cold clouds at all. The search is among the most profound quests in modern science, and it is still underway. We are trying to photograph the birth of the very things that made our kind of birth possible, and beneath all of these specific puzzles lies a more general, more humbling truth. Even setting aside the first stars and the giants and the universal recipe, we still cannot do the one thing that would prove we truly understand star formation. We cannot predict it. Hand a theorist a detailed map of a molecular cloud, its density, its temperature, its magnetic field, its turbulence, everything we can measure, and ask a simple question. Where exactly and when exactly will the next stars form, and how big will they be? And the honest answer is that we cannot say with confidence. The most sophisticated computer simulations of collapsing clouds, running on the most powerful supercomputers, capturing gravity and gas pressure and magnetic fields and turbulence and radiation all at once, still cannot reproduce the full process from first principles without assumptions and adjustments. They get pieces right. They capture the broad strokes, but the complete, predictive, bottom-up theory of star formation, the kind of clean, confident understanding we have for, say, the orbits of the planets, simply does not yet exist. Star formation sits at the crossroads of too many tangled physics. Gravity, magnetism, turbulence, chemistry, radiation, all coupled together across an enormous range of scales, from the vast cloud down to the tiny protostar, and weaving them into a single coherent predictive framework has defeated every attempt so far. We have a story, a rich and detailed and largely correct story, the very story we have been telling. But a story is not the same as a theory that can predict, and the gap between the two is where the deepest mysteries still live. There is another argument that has divided astronomers for decades, and it goes right back to the villain of our story, the magnetic field. We spent a great deal of time earlier on the idea that magnetic fields support clouds against collapse, threading through the gas, anchored to the charged particles, holding the cloud up like an invisible scaffold, and slowly leaking away through the patient seepage of ambipolar diffusion. For a long time, that picture, the strongly magnetized, magnetically supported cloud, rationing out its stars as the field slowly slips away, was the leading theory of how star formation is controlled. But not everyone agreed. A rival camp argued that the magnetic fields, while real, are too weak to be the main controller, and that the true master of star formation is turbulence, the violent, chaotic, supersonic churning of the gas. In this competing view, clouds are not gently held up by magnetism for long ages. They are stirred and shocked by turbulence into a froth of dense knots, and stars form quickly wherever the turbulence happens to pile the gas high enough. These two pictures, magnetically controlled and slow versus turbulence controlled and fast, make different predictions about how clouds behave, how long they live, and how their fields should be arranged. And astronomers have spent enormous effort trying to measure the real strength of the magnetic fields in clouds, using the subtle tricks we discussed earlier, the faint splitting of spectral lines and the delicate polarization of starlight by aligned dust grains. The measurements are fiendishly difficult, and the results have been argued over for years. Some clouds appear strongly magnetized, some weakly. The honest state of affairs is that the balance between magnetism and turbulence, which one truly governs the birth of stars, and by how much, is still not settled. The antagonist of our story may be the master controller, or it may be a supporting player overshadowed by turbulence. Decades into the investigation, the case is not closed. Tied up with that dispute is a deceptively simple question that turns out to be ferociously hard to answer. How long does a molecular cloud actually live? You would think this would be straightforward. Find a cloud, figure out its age, done. But clouds do not carry timestamps, and the methods for estimating their lifetimes are indirect and contested. One school of thought holds that clouds are long-lived structures, persisting for tens of millions of years, slowly and inefficiently dribbling out stars over a great span of time, held together and held back by magnetic fields across many, many free-fall times. The opposing school holds that clouds are fleeting, transient things, assembling rapidly, bursting into star formation almost immediately, and then being torn apart by the feedback of their own newborn stars within just a few million years, born, productive, and destroyed in a cosmic instant. The difference between these two pictures is enormous. In one, star formation is a slow, stately, regulated process. In the other, it is fast, violent, and self-limiting. And the strange thing is that the observations can be read to support either view, depending on the assumptions you bring. The lifetime of a cloud, one of the most basic numbers you could possibly want to know about star formation, remains genuinely uncertain, argued over in the literature, a number that shifts depending on whom you ask and how they counted. Something is wrong with our assumptions somewhere in this debate, because two careful camps of brilliant scientists, looking at the same sky, still cannot agree on how long the nurseries of the stars endure. And here is a subtle, beautiful wrinkle folded inside that debate. The question of whether star formation is contagious. When we looked at the pillars of creation and the cosmic cliffs, we saw massive stars carving into their clouds, and we noted that their radiation can compress the gas ahead of it and possibly trigger new stars to form. This is the idea of triggered star formation, that the birth of one generation of stars can ignite the birth of the next. Like a fire spreading from one patch of dry grass to another, a wave of creation rippling outward through a cloud as each burst of newborn stars squeezes the gas around it into collapse. It is an attractive idea, and there is suggestive evidence for it in certain regions, where rows of young stars seem to march outward in age from a central cluster, the youngest at the expanding edge, as if a wave of formation were sweeping through, but proving that a given star was truly triggered by its neighbours, rather than simply forming on its own at around the same time, is extraordinarily difficult. The signatures are ambiguous. Correlation is not causation. So the degree to which star formation spreads like a contagion versus the degree to which it simply happens spontaneously all across a cloud at once remains another open and actively debated question. We can see that the nurseries are full of feedback, full of stars reshaping the gas around them. What we cannot yet pin down is exactly how much of the next generation is the deliberate child of the previous one, born from the violence of its elders, and how much would have formed anyway. Now let us turn the telescope the other way, away from the giants and toward the smallest things that the clouds produce, because the bottom of the recipe holds its own deep mystery. We have spoken of the failed stars, the brown dwarfs, objects too small to ignite hydrogen fusion in their cores, dim and cooling and destined to fade. And below even the brown dwarfs lie objects smaller still, bodies with masses down around that of the planet Jupiter, drifting alone in the clouds, bound to no star, free-floating in the dark. The James Webb Space Telescope and other instruments have begun to find these tiny objects in the youngest nurseries. Planetary mass bodies adrift on their own, and their existence raises a question that cuts to the very definition of what a star is and how the process that makes stars knows when to stop. Does the collapse of a cloud naturally produce objects all the way down to planetary masses? Is there a smallest possible object that the cloud can make directly, a floor beneath which collapse simply cannot go? And how do we even classify a Jupiter mass object that formed alone, in the dark, out of a collapsing cloud fragment, rather than within the disk around a star? Is it a planet, a failed star, or something that needs a new name entirely? The discovery in the Orion Nebula of pairs of Jupiter mass objects, orbiting each other in the void with no star anywhere near them, deepened the mystery into something close to bewilderment, because our theories of how clouds collapse do not comfortably explain how such tiny objects could form in bound pairs, drifting together through the nursery. They should not be there, according to the simplest expectations, and yet there they are, the very bottom of the star-forming process, the smallest things the cold clouds can make, and how they make them is as murky and contested as the top. We do not fully understand the giants, we do not fully understand the dwarfs, and we do not fully understand where, if anywhere, the process truly stops. There is one more mystery, and in some ways it is the most fundamental of all, because it concerns the very first step of the entire story, the step that comes before everything else we have discussed. We have spent this whole journey assuming the existence of the cold molecular cloud as our starting point. We described its composition, its temperature, its collapse, but we never truly asked where the cloud itself came from. And it turns out that this question, how a cold, dense molecular cloud oscilles in the first place, is itself one of the great unsolved problems. Because most of the gas in a galaxy is not in cold molecular clouds at all. The bulk of the interstellar medium is far more diffuse, far warmer, spread thin across enormous volumes. A tenuous fog of atomic hydrogen, hundreds of degrees warm or warmer, far too sparse and far too hot to ever collapse into a star. For star formation to begin, this thin, warm atomic fog must somehow be gathered together, compressed and cooled, transformed from a diffuse warm haze into the dense, frigid, molecular gas that can finally give birth to stars. And exactly how nature accomplishes that transformation on the grand scale of a galaxy is not fully understood. Think about the difficulty. To turn warm atomic gas into a cold molecular cloud, you have to do several hard things at once. You have to sweep up gas from a vast region and pile it into a much smaller volume, increasing its density enormously. You have to let it cool, radiating away its heat, dropping from hundreds of Kelvin down toward the frigid 10 Kelvin of a true molecular cloud, and you have to shield it, because the molecules that define a molecular cloud, the hydrogen molecules and the carbon monoxide and the rest, are fragile, easily shattered by the harsh ultraviolet starlight that pervades the galaxy. Only once enough gas and dust has piled up to block that destructive radiation can molecules survive and accumulate in the dark interior. So the formation of a molecular cloud is a chicken and egg problem of compression, cooling, and shielding, all of which have to come together in the right order, in the right place, out of a thin warm medium that resists all three. How does the galaxy pull it off? Astronomers have proposed several mechanisms, and again, the truth is probably a combination. The grand spiral arms that sweep through galaxies like ours may act as cosmic traffic jams, slowing and piling up the gas as it flows through them, compressing the diffuse medium enough to begin the transformation, which is why the spiral arms of distant galaxies blaze with the light of newborn stars, tracing out the pattern in brilliant blue. Great expanding bubbles, blown by the winds and explosions of previous generations of stars, may sweep up shells of gas at their edges, compressing the medium as they expand and seeding the next round of cloud formation in their walls. And streams of gas flowing through the galaxy may simply collide with one another, the colliding flows shocking and compressing the gas at their interface, triggering the cooling and the gathering that builds a cloud. Each of these processes surely plays a part, but weaving them into a complete account of how, when, and where the galaxy converts its thin, warm gas into the cold, dense nurseries of the stars, and doing it in a way that predicts the right number of clouds, of the right sizes, in the right places, remains an active frontier. We do not have a finished theory of cloud formation, any more than we have a finished theory of star formation. The mystery does not begin with the collapse of the cloud. It begins one step earlier, with the assembly of the cloud out of almost nothing, out of a warm and reluctant fog that, by every rule we know, should resist becoming cold. And so the chain of mysteries runs all the way down, link after link, each one unresolved. How does the thin, warm gas of the galaxy gather into a cold cloud? We are not sure. How long does that cloud then live? And what controls it, magnetism or turbulence? We are not sure. How efficiently does it convert its gas into stars, and why so little? We are not sure. In what proportions does it make stars of different sizes, and why is that recipe so universal? We are not sure. How do the largest stars grow so big against their own light, and how do the smallest objects form at all? We are not sure. And how did the very first stars ignite, in a universe that had no cold clouds to begin with? We have never even seen it. Every link in the chain that leads from a galaxy of warm gas to a sky full of stars contains a genuine, stubborn, unsolved mystery. We have traced the whole sequence. We have photographed nearly every stage, and we still cannot fully explain a single link of it from first principles. This is the strange and humbling reality at the center of one of the most fundamental processes in all of nature. And there is a hidden hand reaching into the very deepest, darkest parts of the clouds, a force we have barely mentioned, but which may quietly govern much of what happens inside. Deep in the heart of a molecular cloud, shielded from starlight by curtains of dust, you might imagine the gas is completely cut off from the outside universe, sealed in perfect darkness. But it is not. There is one thing that penetrates even the densest shielding, one messenger that reaches all the way into the frozen core where no light can go, cosmic rays. These are not rays of light at all, but high-energy particles, atomic nuclei and electrons, accelerated to nearly the speed of light by distant supernovae and other cosmic catastrophes, racing through the galaxy in all directions. And they are so energetic that they punch straight through the dust, that stops ordinary light, burrowing into the heart of the cloud where nothing else can reach. There, in the dark, they collide with the gas and ionize it, knocking electrons free, leaving behind a trace of charged particles even in the coldest, most shielded depths. And that faint trace of ionization, deep in the core, turns out to matter enormously. It drives the chemistry, enabling the reactions that build the molecules we use to study the cloud. And, crucially, it controls how tightly the magnetic field grips the gas. Remember that the field can only hold onto the gas through the charged particles. The neutral atoms slip free. The level of ionization deep in the core, therefore, sets the pace of ambipolar diffusion itself. The slow CETA we said that rations out the birth of stars. The more cosmic rays penetrate and ionize, the more tightly the field clings, and the slower the gas can collapse. The fewer, the faster. Cosmic rays, in other words, may be a hidden master dial, controlling the rate of star formation in the darkest hearts of the clouds. And here is the problem. We do not know, with any precision, how many cosmic rays actually reach the inside of a given cloud. The rate at which cosmic rays ionize the gas deep in a core is one of the most poorly measured quantities in the whole field, uncertain by large factors, varying from place to place in ways we cannot fully predict. The clouds may shield themselves from cosmic rays to some degree, deflecting them with their own internal magnetic fields, so that the deepest cores are even more isolated than we thought, or they may not. A quantity that may help set the very pace of star birth, the ionization deep in the core, is a number we can barely pin down. It is yet another hidden variable, another dial we know is there, turning somewhere in the dark, without being able to read where it is set. The deeper we look into the machinery of star formation, the more such hidden dials we find. The magnetic field strength, the turbulent energy, the cosmic ray flux, the chemistry of the ices, each one influencing the outcome, each one difficult to measure, each one varying from cloud to cloud. It is a machine with a dozen hidden controls, running in the dark, and we are still trying to read the settings of even the most basic ones. And perhaps that is the most honest way to describe where the science stands today. We have learned to stand outside the machine and watch it run. We have learned to photograph its output in exquisite detail, but we have not yet learned to open it up and read every dial. And until we can, the deepest workings of star birth will keep a part of themselves hidden from us. So the next time you see one of those glorious telescope images, the pillars lit from within, the cosmic cliffs, the glowing nurseries scattered with newborn suns, hold two thoughts in your mind at once. The first is wonder at how much we have learned, how far we have peered into the dark, how much of this hidden process we have dragged into the light. And the second is humility, because behind the beauty of those images lie questions we still cannot answer. Why the recipe is always the same, why the clouds are so reluctant to make stars, how the giants grow so large, how the very first stars were born from a universe with no cold at all, and whether we will ever be able to look at a cloud and truly say, with certainty, what it will become. The birth of stars is at once the best photographed and least understood process of its scale in the cosmos. We have the pictures. We are still searching for the meaning behind them, and that gap, that lingering mystery at the heart of the most fundamental act of creation in the universe, is what makes this one of the greatest unfinished stories in all of science. Step back now, as far back as it is possible to step, and look at this whole process from the largest possible vantage, the scale of the entire universe across the entire span of cosmic time. Because the birth of stars is not just a local curiosity, not just a beautiful thing happening in scattered nurseries here and there. It is the central engine of the cosmos. It is the process that took a universe of cold, dark, formless gas and turned it into everything we see. Every galaxy, every star, every planet, every atom heavier than hydrogen and helium, every living thing. When you understand star formation, you are not just understanding how a single sun lights up. You are understanding how the universe builds itself, how it transforms raw gas into structure and light and chemistry and eventually life. Everything that matters to us traces back, link by link, to the birth of stars. Consider what the universe was like before stars. In the beginning, after the first hot, dense moments cooled and settled, the cosmos was a vast, dark expanse of gas. almost entirely hydrogen and helium, with no heavier elements at all, spread out in the darkness with no source of light beyond the fading afterglow of the birth of the universe itself. There were no stars, there were no galaxies as we know them, there was no carbon, no oxygen, no iron, no silicon, no gold. There were no planets, because there was nothing solid to build a planet from. The universe was a dark, simple, empty-seeming place, full of potential but barren of structure. And then the first clouds collapsed, the first stars ignited, and the great transformation began. Every heavy atom in existence, the calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon that forms the backbone of every molecule of life, the silicon and the metals in the device you are using right now. Every single one of those atoms was forged in the heart of a star, or in the explosion of a dying star, and then scattered out into space to be gathered into the next generation of clouds, and the next generation of stars, and eventually into planets and oceans and living cells. Star formation is the assembly line that manufactures the chemical complexity of the universe. Without it, the cosmos would still be a dark sea of hydrogen, lifeless and unlit forever. Let that sink in. The reason there is anything interesting in the universe at all, the reason there are planets, and chemistry, and life, and minds capable of asking these questions, is that gas clouds learn to collapse into stars. It is worth pausing on this, because the detail is even more astonishing than the broad statement. The elements were not all made in the same way, or at the same time, or by the same kind of star. The periodic table is, in effect, a map of cosmic history, each element bearing the signature of where and how it was forged. The lightest elements, after hydrogen and helium, the carbon and the nitrogen and much of the oxygen, were cooked gently in the cores of ordinary stars, and in the swollen, dying envelopes of stars, somewhat like our sun, in their final stages, then puffed out softly into space. The heavier elements up to iron were forged in the cores of massive stars and blasted out in the titanic explosions of supernovae, the violent deaths of the giants. And the very heaviest elements of all, the gold, the platinum, the uranium, the rare and precious metals, required conditions so extreme that they may be made primarily in the most cataclysmic events the universe can produce, the collisions of dead stars, the smashing together of neutron stars, in bursts so violent they ripple the fabric of spacetime itself. Every one of these processes depends, ultimately, on star formation, because none of it can happen until the stars are born in the first place. The cold clouds make the stars and their deaths make the elements enrich the next clouds, and the cycle turns again, building ever greater chemical richness with each revolution. So when you hold a piece of gold, you are holding atoms that were very likely born in the collision of two dead stars, an event of unimaginable violence, billions of years ago, before the Earth existed. When you breathe in oxygen, you are breathing atoms forged in the hearts of massive stars that lived and died before the sun was born. The calcium in your teeth and bones, the iron that carries oxygen through your blood, the carbon that forms the very structure of every cell in your body. Each element has its own cosmic biography, its own story of which kind of star made it and how that star died to release it. And all of those stories begin in the same place. A cold cloud, collapsing in the dark, igniting into a star. You are, quite literally, a walking museum of cosmic history. Your body assembled from atoms manufactured across billions of years by generations of stars that lived and died long before you, each atom delivered to you by the patient, endless recycling of the clouds. The phrase "we are made of stardust" is not poetry. It is the plain, literal, chemical truth, and the birth of stars is the first chapter of how it came to be. But here is something that very few people realize, a fact that casts this entire story in a wistful, almost melancholy light. The great age of star formation is already over. The universe is past its peak. If you measure the rate at which the cosmos as a whole has been forming stars across its history, counting up all the new stars being born per year in all the galaxies, across all of space, you find that this rate was not always what it is today. Long ago, when the universe was young, just a few billion years after its birth, the cosmos blazed with star formation at a furious pace, building new stars many times faster than it does now. Astronomers call that era the high noon of cosmic star formation, a time billions of years in the past, when galaxies were forming stars in tremendous bursts, lighting up the young universe in a frenzy of creation. And since that distant peak, the rate has been falling. Steadily, inexorably, the universe has been making fewer and fewer new stars with each passing eon. We live in the long afternoon of cosmic history, in a universe whose great burst of creativity lies behind it, a universe that is slowly, gently winding down. Why is star formation declining? The answer is at once simple and profound. The universe is running out of the right kind of fuel. Stars are made from cold gas, and every time a star forms, some of that gas is locked away, bound up in long-lived stars that will shine for billions of years, or trapped forever in the dead remnants that stars leave behind, the cooling embers and collapsed cores that never return their material to the cosmos. The galaxy does recycle some of its gas. Dying stars blow much of their material back out into space to be used again. But the recycling is not perfect. With every generation, a little more gas is locked up and removed from circulation, and the reservoir of fresh, cold, star-forming gas slowly dwindles. The fuel that has not yet been used is also, on average, spreading out and growing harder to gather as the universe expands. And so, like a fire that has consumed most of its wood, the universe burns lower and lower. The clouds that remain still form stars, and will for a long time yet. But the grand, galaxy-spanning bursts of creation that lit the early cosmos will never come again. The universe made most of its stars long ago, and what we see now is the long, slow tapering of a process that has passed its prime. Follow this trend to its conclusion, far into the future, and you arrive at one of the most haunting visions in all of science. There will come a time, unimaginably distant but real, when the last cold cloud collapses, and the last new star ignites. And after that, no more stars will ever be born. The reservoirs of star-forming gas will finally be exhausted, locked away in remnants, or dispersed beyond recall, and the great assembly line will fall silent for good. The stars that exist at that moment will live out their lives, the smallest, dimmest red stars burning slowest of all, persisting for trillions of years, far longer than the universe's current age. But one by one, over the eons, they too will burn out, and then the universe will enter its final, lightless epoch, a cold and endless darkness populated only by the dead husks of stars, the slowly cooling embers drifting in an ever-expanding void, with no new light ever to be kindled again. The age of starlight will end. The cosmos we know, full of brilliant suns scattered across the dark, is a temporary phase, a bright, fleeting interval in the vast history of the universe, an interval that began when the first clouds collapsed and will end when the last one does. We happen to live in the middle of that interval, in the era of starlight, when the sky is still full of suns. It will not always be so, and this is what gives the birth of every single star its quiet weight. Each new star is a small victory against that final darkness, a fresh light kindled in a universe that is slowly running out of the ability to kindle them. Each collapsing cloud, each igniting protostar, each glowing nursery is part of a process that is finite, that is beginning and will have an end, that is even now past its peak and gently fading. We are not watching an eternal, inexhaustible fountain of creation. We are watching a magnificent but limited process, burning through a finite supply of fuel, building what structure and light and life it can in the time it has. The clouds will not last forever. The stars will not last forever. The light itself will not last forever. And against that backdrop, the fact that the universe is making stars at all, right now, in nurseries scattered across the sky, the fact that somewhere out there, at this very moment, a cold cloud is collapsing into a new sun that will shine for billions of years, becomes something almost precious. We live in the lit hours of the cosmos, and the birth of stars is what fills those hours with light. And think about what the birth of one particular star meant, our own. 4.5 billion years ago, a fragment of a cold cloud collapsed in an unremarkable corner of an unremarkable galaxy, and our sun was born. It went through every stage we have traced in this story: the collapse, the disk, the jets, the slow ignition, the violent T-towery infancy. And then it did something quietly miraculous. It settled down. It found its balance, that perfect standoff between the crush of gravity and the push of fusion, and it has held that balance, steadily, patiently, for 4.5 billion years. and will hold it for billions more. That steadiness is the gift on which everything we are depends. Life on Earth did not arise in a flash. It took hundreds of millions of years to begin, and billions more to become complex. And through all of that immense span, the sun simply kept shining, neither flaring up to scorch the young Earth nor guttering out to freeze it, a furnace of almost unbelievable constancy. The same disk that fed the newborn sun also left behind its scraps, and from those scraps the planets formed, including the small rocky world where, against staggering odds, the recycled atoms of ancient stars arranged themselves into something that could live and grow and eventually look up. Every sunrise you have ever seen is light from a star that was born the way every star is born, from a cold cloud in the dark, and that has been keeping faith with this planet since long before there was anyone here to be grateful for it. The birth of the sun was, for us, the most important event in the history of the universe, and it was, in the end, just one more cold cloud, collapsing, like countless others across the sky. The same thing that happened in Orion, and in Rho Ophiuchi, and in the Pillars of Creation, the same thing happening right now in nurseries, scattered across every galaxy, happened once, long ago, in the place that would become our home, and the result was everything we have and everything we are. This world, this life, this fragile and astonishing chance to understand where we came from, and to marvel at it, quietly and gratefully, while the light still lasts. There is one more piece to this grand picture, and it brings the whole story home to us in the most personal way imaginable. Of all the things that star formation built, the most improbable, the most precious, and as far as we know the rarest, is us. Not stars, not planets, not even life in its simplest forms, but minds, beings capable of looking up at the sky, of asking where the stars come from, of building instruments to peer into the clouds, of tracing the whole chain of creation backward to its source. The same process that forged our atoms, that built our planet, that lit our sun, also, after billions of years and a long chain of unlikely steps, produced a species that could turn around and comprehend the process itself. The universe, through us, has become aware of how it makes stars. The cold clouds gave rise to suns, the suns gave rise to planets, the planets gave rise to life, and life, on at least one small world, gave rise to curiosity. And now that curiosity reaches back out into the clouds, with telescopes and equations, trying to understand the very thing that made it possible. There is something almost vertiginous in that thought. We are the universe's way of looking at its own birth. We are stardust that learned to wonder where it came from, and every time we point a telescope at a glowing nursery and watch a star being born, we are, in the deepest sense, watching the beginning of our own story, replayed before our eyes. We began this journey with a paradox that seemed almost absurd, that the coldest places in the entire universe, clouds so frigid they hover just a few degrees above the absolute zero of space, are the very places where the hottest objects in existence are born. Clouds colder than anything you could ever touch, giving rise to suns whose cores burn at millions of degrees. It sounded, at the start, like it should be impossible, and in a sense, everything we have learned only deepened that impression. We found that the cloud must fight its own internal pressure, must overcome the resistance of turbulence, must wait out the slow seepage of magnetic fields locked into its gas, must shed its spin through disks and jets, must survive the radiation of its own siblings, and must somehow, against all of these obstacles, fall inward far enough and fast enough to ignite. At every stage, something stands in the way. At every stage, the birth of a star looks less like an inevitability and more like a narrow escape, a victory snatched from the jaws of a dozen forces all conspiring to prevent it. And yet it happens. It happens constantly. It happens everywhere. The sky is filled with the light of stars that should, by all the obstacles in their path, have struggled to be born at all. That is the first lesson hidden in this story, and it is worth carrying with you. The most ordinary thing in the night sky, a star, of which there are more than grains of sand on all the beaches of the earth, is, when you look closely, the product of an extraordinary and improbable chain of events. We tend to think of the common as the simple, the abundant as the easy. But the abundance of stars does not mean their birth is easy. It means only that the universe is vast and patient, and has had a very long time to let the improbable happen again and again. Every star you see is a small triumph over the forces that resist it, and the same is true, only more so, of you. The chain of unlikely events that had to occur for you to exist, the cloud that had to collapse, the sun that had to form and stabilize, the planet that had to assemble from the leftover dust, the chemistry that had to stir into life, the billions of years of evolution that had to unfold under a steady sun. Each link in that chain was improbable, and yet here you are, the end product of the whole sequence, reading these words, understanding them. We are, all of us, improbable in exactly the way the stars are improbable. We are what happens when the universe is given enough time and enough cold clouds. And there is something almost unbearably strange about the fact that we can understand any of this at all. There is no law that says the universe has to be comprehensible. There is no guarantee that beings made of recycled stardust, clinging to a small planet, should be able to work out the physics of how their own star was born, to measure the temperatures of clouds, thousands of light years away, to trace the magnetic fields threading through gas they will never touch, to photograph the very disks from which planets condense. And yet we can. The same process that made us also, somehow, made us capable of understanding it. The cold clouds produced not only stars and planets, but minds. And those minds turned out to be able to reach back across the vast gulfs of space and time and reconstruct the story of their own origins. This is not something we should take for granted. It is, when you stop to consider it, one of the most remarkable facts in all of existence, that the universe gave rise to a part of itself that could look back and comprehend the whole. When we study the birth of stars, the universe is, in a real sense, studying itself. We are the cosmos grown curious about how it came to be. Hold in your mind now the full sweep of what we have travelled through. A vast cold cloud, dark and silent, drifting between the stars, doing nothing for millions of years. A slow gathering, a quiet tipping point, a core that begins at last to fall inward. A protostar buried in dust, flaring with jets, spinning out its disk. The long climb of temperature at the centre, degree by degree, toward the threshold of fusion. And then the moment, the ignition, when the core finally crosses the line and a new star roars to life, flooding its nursery with light, beginning a reign that will last for billions of years. From the coldest dark to the brightest fire, the entire arc of creation, playing out in nurseries scattered across every galaxy in the universe, over and over since the cosmos was young. It is the oldest story there is, older than the Earth, older than the Sun, nearly as old as time itself. And it is still being written, tonight in clouds you cannot see, as new stars take their first breath in the dark. We live in a brief and luminous window of cosmic history, the age when the stars still shine, when the clouds still collapse, when the light has not yet run out. Far in the past lies the fiery dawn when the first stars lit the darkness. Far in the future lies the long, cold night when the last star fades. And we are here, in between, in the lit hours, able to look up and see a sky full of suns and to understand, at least in part, where they came from and where they are going. That is an extraordinary privilege, and a fleeting one. The beings who came before us could not explain the stars. They could only wonder at them. The beings who come long after the last star dies, if any there are, will have no stars left to wonder at. We are among the first to understand, and we live in one of the few eras when there is still so much to see. The night sky we take for granted is a gift of cosmic timing, a view available only during this particular chapter of the universe's life, and we happen to arrive while the lights were still on. So the next time you step outside on a clear, dark night and look up at the scattered stars, try to hold all of this in your mind at once. Each of those points of light is a sun, born from a cold cloud, against the resistance of a dozen forces. In a process, we have spent this whole story trying to understand and still cannot fully explain. Each one is forging the elements that will one day enrich new clouds and new stars, and perhaps new worlds and new life. Each one is a chapter in a story that began before the Earth existed and will continue long after it is gone. And the atoms in your own body, the very stuff you are made of, came from stars like those, born in clouds like those, billions of years before you drew your first breath. When you look at the stars, you are not looking at something foreign and far away. You are looking at your own family. You are looking at the place you came from. You are looking, across the immense distances of space, at the birth of everything you are. it is worth dwelling, at the very end, on that word we started with, impossible. We titled this story around the idea that the birth of stars from cold clouds should be impossible, and, in a strict sense, that framing was a kind of provocation. Of course, it is not truly impossible. The sky is proof that it happens. But the deeper truth the word points to is real. By the simplest reckoning, by the most natural expectations, the birth of a star runs uphill against everything. It requires the coldest matter to make the hottest fire. It requires the most diffuse, tenuous gas in the universe to concentrate itself into something denser than lead at its core. It requires forces of support, pressure and turbulence and magnetism and rotation to be overcome one by one, each of which on its own looks more than strong enough to win. The remarkable thing is not that any single one of these obstacles can be beaten. It is that all of them are beaten, together, every time a star is born, in a process so reliable that the universe has produced uncountable trillions of stars by it. What looks impossible from the outside turns out to be merely difficult, and what is merely difficult, given a universe vast enough and old enough, becomes inevitable. The impossible, repeated endlessly, becomes the ordinary, and that may be the quietest and most profound lesson the stars have to teach. That the line between the impossible and the inevitable is drawn not by the difficulty of a thing, but by the patience of the universe that attempts it. There is a kind of comfort in that, and a kind of challenge. We too are improbable things, attempting difficult things, in a universe that does not promise us success. We too face forces that seem more than strong enough to defeat us. And yet we are here, the improbable made real, the difficult made actual, witnesses to a cosmos that turned cold dust into fire and fire into worlds and worlds, into the very awareness that now contemplates them. If the stars can be born against everything that resists them, perhaps that is a small permission for the rest of us to attempt the difficult things too. The cold clouds are still out there, in the dark between the stars, waiting, gathering, beginning their slow and patient fall toward the light. Somewhere in this galaxy, at this very moment, a cloud is collapsing that will one day become a star, and around that star, perhaps, a world, and on that world, perhaps, in the fullness of time, something that will look up at its own sky and wonder, as we do now, how it all began. The story does not end with us. It runs on into a future we will never see, in clouds whose stars have not yet been born. And in that endless turning of cold into fire, of darkness into light, of dust into worlds and worlds into minds, the universe goes on making the impossible look effortless, one cold cloud, one new star, one small miracle at a time. We are here to witness it. And that, perhaps, is the most remarkable thing of all.